What if the most mysterious thing about the ancient world is not what was built, but what people considered normal? To us, a colossal stone monument, a city carved into a mountainside, or a network of tunnels stretching beneath the earth seems extraordinary. To the people who created them, these may have been practical solutions to everyday problems. That perspective is easy to forget. We look at ancient ruins through the lens of surprise, while their builders saw them through the lens of necessity. Somewhere between those two viewpoints a gap emerged, a gap created by lost knowledge, vanished traditions, and centuries of forgotten context. And within that gap, some of history's greatest mysteries were born. Not because the ancient world was impossible to understand, but because we are trying to understand it without seeing it through ancient eyes. Xi'an City Wall is one of the largest and best preserved military fortifications ever built, standing in the heart of Xi'an, Shaanxi Province, China. Millions of visitors walk its massive ramparts every year, yet few realize that hidden beneath its bricks lies a technological puzzle that continues to fascinate engineers, materials scientists, and historians alike. Stretching nearly 13.7 kilometers around the old capital, rising approximately 12 meters high and reaching up to 18 meters wide at its summit, the wall appears to be a straightforward medieval defensive structure. But when researchers began studying its construction methods in detail, they discovered evidence of engineering sophistication that seems far ahead of what many assume was possible in the 14th century. The deeper scientists look into the wall's materials, drainage systems, geometry, and structural durability, the more difficult it becomes to explain how builders working over 600 years ago achieved such remarkable results without modern technology. The modern investigation of the wall began during restoration efforts in the 20th century. Archaeologists, architects, and structural engineers expected to find ordinary medieval construction techniques. Instead, they encountered a structure whose performance often exceeded modern expectations. Excavations revealed an enormous rammed earth core covered by millions of specially manufactured bricks. Material analyses uncovered unusual binding agents. Hydrological studies exposed an unexpectedly advanced drainage network. Structural surveys showed an astonishing level of geometric precision across a perimeter nearly 14 kilometers long. Rather than solving the mystery, each discovery raised new questions about the knowledge possessed by Ming Dynasty engineers. Perhaps the most intriguing mystery centers on the wall's construction materials. At first glance, the bricks seem ordinary. However, laboratory analysis revealed traces of a unique mortar mixture unlike most medieval building compounds. Scientists discovered that builders mixed slaked lime with sticky rice soup, creating a hybrid organic-inorganic composite material. The key ingredient appears to be amylopectin, a complex carbohydrate found in glutinous rice. When combined with lime, this substance forms microscopic structures that significantly improve strength, durability, and water resistance. Modern material scientists often describe this mixture as one of the earliest examples of engineered composite construction materials. Tests have shown that sticky rice mortar possesses superior bonding strength compared with many traditional lime mortars. Some experiments demonstrated compressive strengths exceeding those of standard historical mortars by significant margins. The material also exhibits remarkable resistance to water infiltration, one of the primary causes of deterioration in ancient masonry structures. What remains unexplained is how ancient builders discovered such a formula in the first place. There is no surviving scientific document describing experimental development. No engineering manual explains why glutinous rice was selected or how the proportions were determined. The mixture appears too effective to be accidental. In modern laboratories, researchers spend years developing composite materials through controlled testing. Yet centuries ago, Chinese builders somehow produced a mortar capable of surviving hundreds of years of rain, frost, temperature fluctuations, and even earthquakes. Comparisons with other ancient building materials make the mystery even more compelling. Roman engineers famously used volcanic ash in their concrete, creating structures that remained standing after 2 millennia. Researchers studying Xi'an's mortar often draw parallels to Roman concrete because both technologies combine natural materials in ways that dramatically improve performance. Yet, while Roman concrete relied on volcanic pozzolans, Xi'an's builders developed an entirely different solution based on organic chemistry. Two civilizations separated by thousands of kilometers arrived at distinct advanced material technologies, each producing structures that outlived countless generations. The wall's extraordinary longevity cannot be explained by mortar alone. Beneath the brick surface lies an immense rammed earth core, constructed through the systematic compression of countless layers of soil. Historical records indicate that each layer was compacted repeatedly before the next was added. Modern geotechnical studies reveal density levels that continue to impress engineers. The resulting structure behaves differently from a solid stone wall. Instead of resisting forces through rigidity alone, it absorbs and redistributes stress throughout its mass. This characteristic becomes particularly important when considering seismic activity. Shanxi province has experienced numerous earthquakes throughout its history, including the catastrophic 1556 Shanxi earthquake, often regarded as the deadliest earthquake ever recorded. Modern estimates suggest a magnitude near 8.0, with casualties potentially exceeding 800,000 people. Entire settlements disappeared, countless structures collapsed, yet substantial portions of Xi'an's defensive system survived. Engineers studying the wall today suggest that the combination of dense rammed earth and flexible masonry may have functioned as a primitive seismic-resistant design. The earthen core absorbs vibration energy while the brick exterior distributes stress. This concept resembles principles employed in some modern earthquake engineering systems. Whether Ming builders consciously understood these effects remains unknown, but the wall's survival raises questions about the depth of empirical knowledge accumulated through centuries of construction experience. Another unresolved puzzle concerns water management. Water is one of the greatest enemies of large earthen fortifications. If rainwater penetrates the interior, erosion gradually weakens the structure from within. Given Xi'an's dimensions, even moderate storms could generate enormous volumes of runoff. Yet the wall has resisted serious water damage for centuries. Detailed surveys have revealed a sophisticated drainage system integrated throughout the structure. Numerous outlets, channels, and slopes direct water away from critical areas. Engineers mapping the system discovered that drainage points were carefully positioned to prevent accumulation. Surface gradients guide water toward designated exits while minimizing infiltration into the core. The precision of this hydraulic design is difficult to explain. Modern civil engineers rely on mathematical models, surveying instruments, and hydraulic calculations when designing drainage systems for large infrastructure projects. Ming engineers possessed none of these tools in their modern form. Nevertheless, they created a network capable of protecting one of the largest urban fortifications in the world. Whether this achievement resulted from advanced practical experience, lost engineering traditions, or sophisticated geometric planning remains a subject of debate. Geometry presents another mystery. Satellite imagery reveals the enormous scale and symmetry of the wall. The enclosure forms an impressively regular defensive perimeter around the ancient city. Maintaining geometric consistency across nearly 14 kilometers would challenge even modern survey teams without proper equipment. Builders of the 14th century lacked GPS, aerial photography, laser measurements, and digital mapping. Yet measurements indicate surprisingly low deviations across major sections of the fortification. Historians believe surveyors relied on astronomical observations, ropes, measuring rods, and geometric principles. However, the level of precision achieved suggests organizational capabilities and technical knowledge beyond what many people associate with medieval construction. The military design of the wall adds another layer to the mystery. Nearly 100 defensive bastions project outward from the main structure. These positions were arranged to maximize overlapping fields of fire, allowing defenders to attack approaching enemies from multiple angles. Military historians often note that the layout minimizes blind spots and optimizes defensive coverage. Such efficiency resembles modern concepts of defensive geometry and operational planning. The arrangement appears less like a collection of independent towers and more like a carefully optimized system. Determining the ideal spacing of defensive positions across a massive perimeter would have required extensive planning. Yet little evidence survives explaining the calculations or design methodologies employed by the engineers responsible. What do you think? Was the extraordinary durability of Xi'an City Wall the result of centuries of accumulated experience, or did Ming engineers possess construction knowledge that has since been lost? Share your thoughts in the comments below. Royal Kurgan is a massive burial mound standing near Kerch on the eastern edge of Crimea, overlooking the narrow strait that links the Black Sea and the Sea of Azov. From the outside, it appears deceptively simple, a low hill of stone and earth rising above the landscape. Yet hidden within this mound is one of the most remarkable engineering achievements of the ancient Bosporan kingdom. More than 2,300 years after its construction in the 4th century BCE, archaeologists are still debating how its builders achieved such extraordinary structural precision, using only the tools available in the classical age. Unlike many ancient mysteries associated with legends or lost civilizations, the mystery of Royal Kurgan is rooted in architecture, mathematics, and engineering knowledge that seems far ahead of what historians can confidently reconstruct. The monument became known to modern scholars during 19th century archaeological investigations of the Kerch Peninsula, a region rich in Greek and Bosporan remains. When excavators entered the mound, they expected a typical elite tomb. Instead, they discovered an astonishing stone passage leading toward a towering burial chamber, whose geometry immediately attracted attention. Although the tomb had been looted in antiquity and much of its original funerary wealth had disappeared, the structure itself survived. Over time, researchers realized that the greatest treasure of Royal Kurgan was not what had been buried inside, but the engineering knowledge embedded within its stones. The most extraordinary feature is the gigantic corbel-vaulted burial chamber. The chamber rises to approximately 8.7 meters in height, equivalent to a modern 3-story building. At first glance, it resembles a true dome. Yet, it is not a dome in the Roman sense. No keystone locks the structure together. Instead, each successive ring of stone projects slightly inward over the layer below it until the opening narrows near the top. This technique, known as corbelling, was used in several ancient cultures, but Royal Kurgan represents one of the most sophisticated examples ever constructed around the Black Sea. The challenge becomes clear when engineers analyze the forces involved. Every stone must transfer its load downward while maintaining equilibrium. If even a small number of blocks were misaligned, the entire chamber could gradually deform and eventually collapse. Yet after more than 23 centuries, the structure remains standing. The obvious comparison is with the famous Tholos tombs of Messenian Greece, especially the treasury of Atreus, built around 1250 BCE. That monument reaches approximately 13.5 meters in height and was long regarded as one of the greatest corbel structures in the ancient world. Royal Kurgan is smaller, but its proportions are exceptionally elegant and precise. Researchers studying the geometry of the chamber have noted that the reduction in diameter toward the top appears highly systematic rather than improvised. The builders seem to have followed a carefully planned mathematical design. This raises an uncomfortable question. How did engineers of the Bosporan Kingdom calculate the stability of such a structure without modern structural mechanics, finite element analysis, or even formalized engineering equations? Ancient builders clearly understood the practical behavior of stone, yet the methods they used to predict long-term stability remain almost entirely undocumented. The mystery becomes even deeper when examining the stone blocks themselves. Many weigh several tons. Their surfaces show evidence of deliberate shaping and careful fitting. Modern measurements reveal surprisingly small gaps between adjacent blocks in critical areas of the chamber. While stone-cutting technology certainly existed throughout the Greek world, maintaining such consistency across an entire monument required remarkable quality control. Experimental archaeology demonstrates that workers using iron chisels and hammers can shape limestone with considerable precision. However, replicating the exact tolerances observed throughout Royal Kurgan would demand not only skilled craftsmen, but also standardized measuring systems. No surviving Bosporan engineering manuals explain how this level of accuracy was achieved. The entrance corridor introduces another layer of mystery. The dromos, or passageway, extends roughly 36 meters toward the burial chamber. Visitors often report a strange visual sensation as they move through it. The chamber appears larger than expected, while the proportions of the corridor seem subtly altered. Architectural historians have suggested that the builders intentionally manipulated perspective. Similar optical refinements are known from classical Greek architecture. The Parthenon in Athens famously incorporates slight curvature in supposedly straight lines because the human eye perceives perfect geometry imperfectly. If Royal Kurgan employs related principles, its architects possess not only engineering expertise, but also an advanced understanding of visual psychology. Such sophistication would place the monument among the most intellectually ambitious structures of the Hellenistic world. Transportation presents another unresolved puzzle. Constructing the monument required thousands of tons of limestone. Every block had to be quarried, shaped, transported, lifted, and positioned with precision. Ancient engineers likely relied on sledges, rollers, ramps, ropes, wooden cranes, and large labor forces. Yet the exact methods remain speculative because no direct construction records survive. Modern engineers attempting to model the logistics estimate that the project would have required extensive planning and coordination. Even a small error in sequencing could have delayed construction or destabilized the partially completed chamber. The absence of written documentation means that the organizational systems behind the project remain invisible. We see the final result, but not the process that produced it. Perhaps even more impressive is the monument's long-term structural durability. Crimea lies within a region affected by seismic activity and significant seasonal temperature fluctuations. Over centuries, countless ancient buildings across Eurasia suffered severe damage from earthquakes, settlement, weathering, or human intervention. Royal Kurgan, however, has survived remarkably well. Some researchers believe the mound itself played a crucial engineering role. Rather than serving merely as a symbolic covering, the surrounding earth may have acted as a stabilizing shell, distributing pressure around the stone chamber and reducing structural stress concentrations. In modern engineering terms, The monument functions as a composite system in which stone and earth work together. Whether the builders consciously understood these principles or arrived at them through accumulated empirical experience remains uncertain. The geometry of the burial chamber has generated particular interest among structural analysts. Computer simulations suggest that corbel structures can remain stable for millennia when the center of mass of each successive layer remains within carefully defined limits. Yet achieving this balance requires remarkable precision. Ancient builders obviously lacked computer models, but they somehow developed construction methods that produced nearly identical outcomes. Similar mysteries appear at sites such as the Treasury of Atreus, Newgrange in Ireland, and certain neuralgic structures in Sardinia. Across vast distances and different cultures, ancient engineers repeatedly created stable stone chambers whose underlying design principles are only partially understood today. Royal Kurgan stands as one of the clearest examples of this phenomenon. Another unresolved question concerns the transfer of knowledge. The Bosporan kingdom existed at the crossroads of Greek, Scythian, and local traditions. Royal Kurgan combines elements from multiple cultural influences, yet the exact origin of its engineering concepts remains debated. Did its builders inherit techniques from earlier Greek architects? Were local craftsmen responsible for innovations adapted to regional conditions? Or did the monument represent the culmination of generations of experimentation now lost to history? The absence of surviving plans, calculations, and technical texts leaves these questions unanswered. What do you think is the most impressive mystery of Royal Kurgan? Was it the giant corbel vault, the remarkable precision of its stonework, or the lost engineering knowledge behind its construction? Share your thoughts in the comments below. Hanoi Old Citadel, known today as the Imperial Citadel of Thang Long in the heart of Hanoi, Vietnam, is one of Southeast Asia's most extraordinary archaeological puzzles. Beneath the crowded streets of a modern city lies a buried capital that functioned continuously for more than 1,000 years. What makes the site remarkable is not simply its political importance, but the sophisticated engineering hidden beneath layers of earth. Archaeologists expected to uncover palace ruins when large-scale excavations began at 18 Huangdiu in 2002. Instead, they found evidence of a vast technological system that had survived on one of the most unstable landscapes in northern Vietnam. The discoveries raised a difficult question. How did ancient builders create a durable capital on soft alluvial soil that still preserved traces of its infrastructure after nearly a millennium? The modern discovery occurred when construction work for Vietnam's National Assembly complex revealed unusual archaeological remains. Excavations eventually exposed more than 19,000 square meters of buried structures, making it one of the largest archaeological investigations ever conducted in Southeast Asia. Researchers uncovered millions of artifacts, including foundations, drainage channels, wells, bricks, ceramics, roads, and palace remains spanning multiple dynasties. Even more surprising was the realization that the same location had been continuously occupied from the Chinese Tang period through the Li, Tran, Le, and Nguyen dynasties. Layer after layer of construction formed a vertical record of urban engineering extending across approximately 13 centuries. The first mystery involves urban planning continuity. In many ancient capitals, political collapse resulted in the abandonment or relocation of the city. Thang Long followed a different pattern. Excavations revealed that major architectural axes remained remarkably consistent despite centuries of warfare, dynastic transitions, invasions, and rebuilding campaigns. Some palace complexes from different eras align with surprising precision. Maintaining such consistency would have required accurate surveying techniques and a method for preserving spatial information across generations. Yet no detailed engineering manuals have survived to explain how these measurements were transferred from one dynasty to the next. The challenge becomes even more impressive when compared with medieval European capitals, where urban layouts often shifted dramatically after periods of destruction. Thang Long appears to have preserved a long-term geometric memory that exceeded what historians once believed possible. Another unresolved question concerns the city's relationship with water. Hanoi sits within the Red River Delta, an environment characterized by flooding, seasonal water fluctuations, and soft sedimentary ground. Modern engineers classify such terrain as challenging for large-scale construction because of subsidence risks. Yet the ancient capital developed into one of the largest urban centers in Southeast Asia. Excavations revealed extensive drainage systems built from bricks and fired clay. Many channels maintained consistent gradients over long distances, suggesting careful hydraulic calculations. The drainage network was capable of directing stormwater away from palace districts, while simultaneously preventing erosion. Similar hydraulic sophistication is often associated with sites such as Angkor in Cambodia or the Roman cities of Europe. However, unlike those civilizations, very few technical records survive from medieval Vietnam. The infrastructure exists, but the knowledge behind it has largely vanished. The foundations themselves present another engineering puzzle. Modern skyscrapers in Hanoi frequently require deep reinforced concrete piles extending tens of meters below ground level. Ancient builders obviously lacked such technology. Nevertheless, archaeological excavations have uncovered palace platforms that remained stable for centuries. Analysis shows that the builders created layered foundation systems consisting of compacted earth, sand, gravel, broken bricks, and ceramic fragments. In modern geotechnical engineering, similar principles are used to distribute loads and reduce differential settlement. Some researchers have described these ancient foundations as an early form of composite ground engineering. The mystery lies in the fact that there is no surviving documentation explaining how builders determined the thickness, composition, or arrangement of each layer. The structures demonstrate sophisticated understanding, but the methodology remains invisible. Among the most revealing discoveries are the bricks themselves. Millions of bricks recovered from the site carry inscriptions identifying production centers, military workshops, or administrative authorities. Many examples show remarkably low dimensional variation. Standardization on this scale suggests centralized quality control. Ancient Rome achieved comparable consistency through imperial brick industries, while China developed state-controlled ceramic production systems. The question is whether medieval Vietnamese authorities operated an equally sophisticated manufacturing network. Some bricks were transported over considerable distances before reaching the capital, yet they maintained similar dimensions and material quality. Archaeologists continue to debate how such standardization was enforced in an era without modern industrial equipment. Perhaps the most fascinating mystery centers on the extraordinary durability of the bricks and roof tiles. Hanoi experiences high humidity, intense rainfall, biological growth, and dramatic seasonal temperature changes. Under such conditions, many construction materials deteriorate rapidly. Yet numerous bricks from the Lian Tran periods remain structurally intact after approximately 700 to 1,000 years underground. Laboratory analyses have identified dense ceramic microstructures, low porosity levels, and evidence of high-temperature firing. Some specimens exhibit mechanical strength comparable to certain modern masonry products. The durability becomes even more remarkable when compared with ordinary fired bricks, which often suffer substantial degradation after prolonged exposure to moisture. Researchers have proposed several explanations, but none fully account for the observed performance. One theory suggests that ancient craftsmen carefully selected clay sources rich in specific mineral compositions. Another argues that firing temperatures exceeded what historians previously assumed for medieval kilns. Microscopic studies reveal highly vitrified zones within some samples, indicating temperatures that may have approached or surpassed 1,000 degrees Celsius. Achieving such temperatures consistently would have required exceptional control of fuel, airflow, and kiln design. Yet the production centres responsible for many of these bricks have never been conclusively identified. The water resistance of these materials creates an even deeper puzzle. Certain bricks recovered from saturated archaeological layers display surprisingly limited structural damage, despite centuries of exposure to groundwater. Modern materials scientists note that durability depends not only on firing temperature but also on pore structure. If pore networks are too large, water penetrates easily and accelerates deterioration. If they are too small and uniformly distributed, moisture damage is significantly reduced. Some ancient Thang Long bricks appear to possess precisely these favourable characteristics. Whether this resulted from deliberate engineering or accumulated craft knowledge remains unknown. Comparisons with other ancient civilizations highlight the significance of the mystery. Roman marine concrete continues to attract scientific attention because its chemical composition allowed it to strengthen over time in seawater. Similarly, the enduring bricks of Thang Long may represent a lost tradition of material optimization. Unlike Roman concrete, however, no surviving written recipes explain how Vietnamese craftsmen achieved these results. The products remain, but the manufacturing process disappeared centuries ago. The site also contains dozens of wells built in different shapes, including circular, square, and polygonal designs. Their placement appears too systematic to be random. Some scholars believe they formed part of an integrated water management network connected to drainage channels and residential districts. Others argue that certain wells held ceremonial or cosmological significance related to palace planning. Because only portions of the ancient city have been excavated, researchers cannot yet reconstruct the complete hydraulic system. Large sections remain buried beneath modern Hanoi, beyond the reach of archaeological investigation. Could the enduring bricks, sophisticated foundations, and advanced water systems of Thang Long be evidence of engineering knowledge far ahead of its time? Tell us what you think in the comments below. Near Nagpur in Maharashtra, India, the ruins of Nagardan Fort conceal a far more remarkable story than their weathered walls initially suggest. For centuries, the site appeared to be just another abandoned hill fort, scattered across the Deccan landscape. That perception changed when archaeological excavations revealed the remains of an ancient urban centre linked to Nandivardhana, one of the capitals of the Vakataka dynasty during the 4th and 5th centuries CE. Beneath layers of soil, researchers uncovered palace complexes, defensive structures, drainage networks, workshops, luxury goods, coins, and evidence of large-scale urban planning. These discoveries transformed Nagardan from a forgotten fortress into a technological mystery. Archaeologists could clearly see the results of sophisticated engineering, yet many of the techniques and methods behind those achievements remain only partially understood. What makes Nagardan particularly intriguing is that it emerged during a period often described as one of ancient India's golden ages. The Vakatakas were contemporaries and allies of the Gupta Empire, a civilization famous for advances in mathematics, astronomy, metallurgy, and architecture. Historians possess inscriptions, artworks, and literary records from the era, yet surprisingly little survives regarding the practical, engineering knowledge used to build and operate major urban centres. Nagadan offers a rare opportunity to examine that missing technological layer. The first mystery begins with the fortress itself. At first glance, the defensive walls seem relatively conventional, but closer examination reveals a level of planning that appears unusually advanced for the period. The positioning of entrances, angles of approach, and defensive sectors suggests that builders understood concepts of battlefield control that would later become fundamental in military architecture. Certain sections appear designed to funnel attackers into predictable paths while exposing them to defenders positioned along elevated walls. Similar principles can be observed in much later fortifications across Asia and Europe. Yet Nagadan predates many of those examples by centuries. The question is not whether ancient engineers could build walls. The question is how they developed such sophisticated defensive geometry without surviving military engineering manuals or documented design traditions. Equally fascinating is the site's urban organization. Excavations indicate that different activities were carefully separated into distinct zones. Administrative areas, residential quarters, storage facilities, and production centers occupied planned spaces rather than developing randomly over time. Modern urban planners understand the enormous complexity involved in organizing a city efficiently. Even today, successful urban layouts require surveying, measurement, logistics, and long-term forecasting. Archaeological evidence suggests that Nagadan's builders achieved comparable results using tools that appear remarkably simple by modern standards. No precision instruments have been found. No engineering blueprints survive. Yet the overall arrangement displays a coherence that implies accurate land measurement and coordinated planning over a substantial area. The mystery becomes even more intriguing when water management enters the picture. Nagadan existed in a region where seasonal rainfall dominates the annual water cycle. During monsoon months, large quantities of water arrive rapidly. During dry periods, water becomes a precious resource. Ancient cities often rose or fell based on their ability to manage this challenge. Excavations at Nagadan reveal reservoirs, drainage channels, collection systems, and hydraulic infrastructure designed to regulate both excess water and scarcity. Modern hydrological models demonstrate that even minor miscalculations in reservoir capacity, channel gradient, or drainage volume can lead to catastrophic failure. Yet the settlement appears to have functioned successfully for generations. Researchers can observe the infrastructure itself, but the mathematical principles and accumulated engineering experience behind its design remain largely invisible. The drainage systems present another unresolved puzzle. Across the ancient world, effective drainage was one of the most difficult engineering problems. Water infiltration weakens foundations, damages walls, accelerates erosion, and can ultimately destroy entire settlements. Cities such as Mohenjo-Daro became famous for remarkably advanced drainage networks more than a millennium earlier. Nagadan appears to continue that tradition of hydraulic sophistication. Some excavated channels suggest deliberate attempts to control runoff and prevent structural damage. The builders clearly understood how water moved through the landscape. What remains unclear is how this knowledge was transmitted across generations and whether it existed as formal engineering doctrine or as practical expertise accumulated through centuries of experimentation. The construction materials themselves raise further questions. Archaeologists have identified extensive use of fired bricks produced on a scale that implies organized manufacturing. Many surviving examples display dimensions that remain surprisingly consistent. Achieving such standardization without mechanized production is difficult. Modern industrial systems rely upon molds, quality control procedures, measurement standards, and continuous supervision. Ancient brickmakers possessed none of these advantages, yet evidence suggests they were able to produce large quantities of building materials with relatively little variation. This consistency hints at the existence of technical standards that governed construction projects throughout the settlement. Some researchers argue that standardization may be one of the strongest indicators of technological sophistication. In engineering, repeatability often matters more than isolated innovation. A civilization capable of producing thousands of nearly identical construction components possesses a level of organizational and technical discipline that extends beyond simple craftsmanship. The mystery is that no written technical codes from Nagardan have survived. The physical evidence suggests standards existed. The documents that explained those standards have vanished. Beneath all of these achievements lies an even deeper question: labor organization. Large-scale construction projects require more than engineering knowledge. They demand administration, logistics, scheduling, supply chains, workforce management, and resource allocation. Modern infrastructure projects rely upon computers, communication networks, written records, and specialized management systems. Ancient Nagardan possessed none of these technologies. Nevertheless, it successfully coordinated the construction of fortifications, public buildings, water systems, and urban infrastructure. Archaeologists can estimate the volume of material moved, the labor required, and the complexity of the finished structures. What they cannot fully explain is the organizational mechanism that made such projects possible. Comparisons with other ancient centers make the puzzle even more striking. The Roman Empire left extensive written records describing aspects of engineering and construction. Ancient China preserved technical manuals covering architecture, hydraulics, and administration. In contrast, much of the practical engineering knowledge behind Nagardan appears to have disappeared. The city survives as evidence of technological capability, yet the intellectual framework that produced those achievements remains largely absent from the historical record. It is similar to discovering a modern aircraft while losing every manual, formula, and training program associated with its creation. Excavated artifacts add another layer to the mystery. Luxury objects, coins, ornaments, and imported materials indicate that Nagardan participated in broader economic networks extending across the Indian subcontinent. Such trade connections required reliable roads, storage systems, taxation mechanisms, and administrative oversight. The city was not an isolated fortress. It functioned as a regional hub integrated into a larger political and economic landscape. The sophistication implied by these networks further reinforces the impression that a substantial body of technical and administrative knowledge once existed here. Located in Jiji Township, Nantou County, central Taiwan, Wuchang Temple sits only a short distance from the Chelungpu Fault. Unlike most ancient mysteries, its puzzle is not hidden in a forgotten civilization or buried beneath centuries of sediment. It is preserved in plain sight. On September 21, 1999, the magnitude 7.6 Chi-Chi earthquake struck Taiwan and transformed the temple into one of the most unusual engineering mysteries of the modern era. More than 25 years later, researchers still debate exactly why the structure collapsed in the manner it did. The disaster was witnessed, photographed, measured, and recorded by modern instruments. Yet the ruins continue to expose limits in our understanding of earthquakes, structural behavior, and geological forces. The temple itself was built in 1923 and served as an important religious center for decades. Following the earthquake, engineers arrived expecting to study a conventional collapse. Instead, they encountered something that appeared almost impossible. Large portions of the upper structure remained recognizable, while much of the lower support system had been crushed beneath it. The result resembled a carefully staged demolition rather than the chaotic destruction normally associated with major seismic events. Because the collapse occurred during one of the best documented earthquakes in Asian history, Wuchang Temple became an unexpected scientific case study. The Chi-Chi earthquake remains one of the most extensively researched seismic disasters ever recorded. Originating along the Cheongpu Fault, the rupture extended approximately 100 kilometers across central Taiwan. Measurements revealed vertical ground displacements exceeding 2 meters in some locations and horizontal movements approaching several meters. Instruments recorded peak ground accelerations greater than 1 g in certain areas, meaning parts of the landscape briefly accelerated faster than gravity itself. Such forces are capable of throwing vehicles into the air and tearing apart foundations. Yet even under these extreme conditions, the exact destruction pattern observed at Wuchang Temple remains difficult to reproduce through computer simulation. One explanation centers on resonance, a phenomenon familiar to engineers and physicists. Every structure possesses natural frequencies at which it vibrates most efficiently. When earthquake waves match those frequencies, structural motion can become dramatically amplified. Similar effects were observed during the 1985 Mexico City earthquake, where buildings hundreds of kilometers from the epicenter collapsed because seismic waves resonated with their natural vibration periods. Researchers suspect that Wuchang Temple may have experienced a comparable effect. However, the situation was far more complicated because multiple seismic wave types arrived simultaneously. Fast-moving primary waves, destructive secondary waves, and slower surface waves interacted with local geology before reaching the structure. The resulting vibration pattern may have produced an extremely rare combination of forces concentrated in specific sections of the building. The geological setting introduces another layer of complexity. Earthquake engineering traditionally assumes that foundations remain relatively continuous even while shaking violently. During the Chi-Chi earthquake, the ground itself was changing shape. Sections of the fault physically displaced the landscape. In some areas, roads buckled, bridges fractured, and entire stretches of terrain shifted position. This distinction is crucial. Engineers can design buildings to withstand vibration. Designing them to withstand the sudden deformation of the earth beneath them is significantly more difficult. Wuchang Temple may therefore represent a collision between structural engineering and geological processes operating beyond normal design assumptions. Comparisons with other major earthquakes reveal why the site continues to attract scientific attention. During the 1995 Kobe earthquake in Japan, approximately 6,400 people died and thousands of buildings collapsed. Investigators were generally able to identify the primary causes of failure, including inadequate reinforcement and outdated construction standards. During the 2011 Tohoku earthquake, researchers gained unprecedented insight into how modern infrastructure responds to seismic events of magnitude 9.0. Yet Wuchang Temple presents a different challenge. Scientists possess abundant data, photographs, geological surveys, eyewitness testimony, and structural evidence. The problem is not a lack of information. The problem is that the available information does not produce a single universally accepted explanation. Perhaps the most striking feature of the ruins involves the survival of numerous statues inside the temple. Visitors frequently focus on these artifacts because they remained far less damaged than surrounding structural elements. To believers, the survival appears miraculous. To engineers, it raises questions about force distribution during collapse. Modern disaster investigations have documented similar phenomena in earthquakes, landslides, avalanches, and building failures. During collapse, temporary voids sometimes form within debris fields. These spaces can shield objects from crushing forces even when surrounding structures are destroyed. The challenge lies in predicting where such zones will appear. Current models can estimate probabilities but cannot reliably forecast the exact location of survival pockets within a collapsing building. The temple also provides evidence for a phenomenon known as seismic energy focusing. Earthquakes release enormous quantities of energy, yet that energy rarely spreads evenly across the landscape. Geological layers can amplify, redirect, or concentrate seismic waves. Scientists often compare the process to light passing through a lens. In Mexico City, soft lakebed sediments amplified earthquake waves so effectively that buildings more than 350 kilometers from the epicenter suffered catastrophic damage. Similar amplification effects may have occurred near Wuchang Temple. Local soil conditions, sediment thickness, and subsurface rock geometry could have concentrated destructive energy beneath the site. Determining the precise contribution of these factors remains an active area of investigation. Another unresolved issue concerns nonlinear structural behavior. Modern engineering software can model millions of calculations per second, yet complex systems often behave unpredictably once critical thresholds are crossed. Small differences in material quality, construction techniques, foundation conditions, or vibration timing can produce dramatically different outcomes. This sensitivity resembles chaos theory in meteorology, where tiny variations in atmospheric conditions can lead to significantly different weather patterns. Wuchang Temple demonstrates that earthquakes operate under similar principles. Researchers may understand individual components of the process, yet the interaction between these components can generate outcomes that remain extraordinarily difficult to predict. The preservation of the ruins transformed the site into something rare, a full-scale earthquake laboratory. Most damaged structures are demolished shortly after disasters. Wuchang Temple was left largely intact as a memorial and research site. As a result, scientists can examine actual collapse patterns rather than relying solely on laboratory experiments or computer-generated models. Every fractured column, displaced beam, and surviving wall provides data about how real structures behave under extreme seismic loading. Few earthquake sites offer such a complete physical record. Stories that emerged after the disaster further enhanced the temple's reputation. Visitors reported unusual observations involving statues, sacred objects, and decorative features. Among the most famous claims was that certain statue beards appeared to continue growing after the earthquake. No scientific evidence supports the phenomenon, and specialists generally attribute such observations to maintenance, humidity-related material changes, or visual perception. Nevertheless, these stories highlight an enduring reality. Whenever science encounters unanswered questions, mythology often emerges alongside it. Wuchang Temple became a place where engineering uncertainty and cultural belief coexist. Bunjikat is a forgotten capital buried among the mountains of present-day Tajikistan. Yet hidden beneath its eroded walls lies a mystery that challenges everything we think we know about ancient engineering. More than 1,200 years ago, builders in this remote valley created a thriving city filled with palaces, fortifications, hydraulic systems, and vibrant murals whose colours still survive today. They did so in one of the most earthquake-prone regions of Central Asia, without modern surveying equipment, chemical laboratories, or advanced machinery. The ruins of Bunjikat do not simply tell the story of a lost kingdom. they preserve evidence of technical knowledge that archaeologists are still struggling to fully explain. The discovery of Bunjikat emerged through archaeological investigations conducted during the 20th century in the Shahristan region of northern Tajikistan. Excavations revealed that the site had once been the capital of Ustrashana, a powerful kingdom that flourished between the 5th and early 9th centuries CE. Beneath layers of collapsed earth, researchers uncovered palace complexes, defensive walls, residential districts, temples, workshops, and some of the finest mural paintings ever found in Central Asia. At first glance, Bunjikat appears similar to many ancient Silk Road cities, but the deeper archaeologists investigated, the more unusual the site became. The city was constructed in a mountainous environment that presented severe logistical challenges. Annual precipitation in parts of the region can be less than 300 millimeters, and the surrounding terrain offers limited agricultural land compared with the fertile river valleys that supported cities such as Mesopotamian Babylon or Roman Antioch. Despite these disadvantages, Bunjikat developed into a major political centre capable of supporting thousands of inhabitants. The first puzzle concerns water. Every large ancient city depended upon reliable access to fresh water. Rome built aqueducts stretching hundreds of kilometres. The Nabateans at Petra engineered sophisticated channels and reservoirs to survive in the desert. Yet Bunjikat occupied a location where sustaining a large urban population should have been extremely difficult. Archaeological surveys have identified remnants of canals, reservoirs, and irrigation systems, but the complete hydraulic network remains unknown. Many channels have disappeared beneath later sediments or modern settlements. Researchers know that the city functioned successfully for centuries, but they still cannot fully reconstruct how water was captured, distributed, and stored with enough efficiency to sustain an urban centre in such a demanding environment. The city's architecture introduces another mystery. Bunjikat stood within a region affected by frequent seismic activity. Modern Tajikistan experiences earthquakes generated by the ongoing collision between the Indian and Eurasian tectonic plates. Throughout history, destructive seismic events have repeatedly struck Central Asia. Yet many structures at Bunjikat display design principles that appear remarkably effective at resisting earthquake damage. Excavated buildings reveal thick rammed earth walls, layered foundations, flexible construction materials, and carefully distributed structural loads. In some cases, organic fibres were mixed into building materials, creating a composite structure capable of absorbing stress. Similar concepts are employed in modern earthquake-resistant engineering, where flexibility can be more important than rigidity. The question is not whether the builders understood plate tectonics, they certainly did not. The question is how centuries of empirical observation allowed them to develop architectural solutions that mirror principles recognized by modern structural engineers. Some researchers suggest that repeated reconstruction after earthquakes gradually produced increasingly resilient designs. Others argue that regional traditions preserved technical knowledge accumulated over generations and transmitted among specialized builders. The defensive system of Bunjikat presents equally intriguing questions. The city occupied strategically elevated terrain and incorporated multiple layers of fortifications. Archaeological mapping reveals an arrangement that maximized visibility across surrounding approaches while minimizing vulnerable blind spots. Defensive walls, towers, and elevated positions created overlapping observation zones that would have made surprise attacks extremely difficult. Modern geographic information system analysis has demonstrated how efficiently the fortifications exploited natural topography. What remains unclear is how ancient planners achieved such optimization without access to aerial surveys, contour maps, satellite imagery, or modern instruments? Similar questions have been asked about the hilltop defences of Iron Age Europe and the Inca stronghold of Machu Picchu. At Bunjakat, however, the integration between terrain and fortification appears unusually sophisticated for a city often overlooked in broader discussions of ancient military engineering. The palace associated with the rulers of Ustrashana provides another layer of mystery. Excavations uncovered ceremonial halls, reception chambers, corridors, and richly decorated interiors. What astonished researchers was the geometric precision evident throughout the complex. Rooms align along carefully planned axes despite uneven terrain and challenging construction conditions. Modern builders achieve such precision using laser levels, surveying equipment, and standardized measurement systems. Ancient builders relied upon ropes, plumb lines, sighting methods, and accumulated experience. Yet measurements from excavated structures suggest that construction followed highly organized planning principles. The exact surveying techniques used by the architects remain largely unknown because the tools themselves have rarely survived. The results are visible everywhere, but the methods remain frustratingly elusive. The most fascinating mystery at Bunjakat involves its extraordinary murals. This is where the site becomes truly unique. The palace walls once displayed vibrant paintings depicting rulers, warriors, religious figures, musicians, mythological scenes, and ceremonial events. Although more than 12 centuries have passed since their creation, many pigments retain remarkable colour intensity. Reds, blues, yellows, blacks and whites continue to survive despite exposure to environmental degradation, structural collapse, and the passage of time. Scientific analysis has identified mineral pigments derived from local and imported materials. Iron oxides likely contributed reds and browns. Carbon-based compounds produced black pigments. Other colours appear to have required more sophisticated preparation techniques involving mineral processing and carefully controlled mixtures. Yet identifying ingredients is only part of the challenge. The greater mystery lies in the manufacturing process itself. Modern conservation science can often determine the chemical composition of ancient pigments. Reconstructing the exact production methods is far more difficult. Temperature control, grinding techniques, binding agents, layering procedures, and curing methods all influence the final appearance and durability of paint. Even when scientists know what materials were present, they frequently cannot reproduce identical results without understanding the original manufacturing sequence. This phenomenon is not unique to Bunjakat. Similar challenges exist with Roman concrete, Chinese imperial porcelains, and certain Egyptian pigments. At Bunjakat, however, the murals demonstrate a level of durability that suggests highly refined artistic technology. Some pigments remained stable for more than a millennium in an environment characterized by seasonal temperature fluctuations, moisture variation, and structural instability. Particularly puzzling is the possibility that some binding agents contained complex organic compounds that have largely degraded over time. These substances may have played a critical role in preserving colour saturation and adhesion. Because organic materials decompose far more readily than minerals, much of the evidence needed to reconstruct the complete process has vanished. The murals also reveal extensive cultural connections across Eurasia. Certain artistic influences resemble Persian traditions. Others show links to Indian, Central Asian, and even Chinese visual styles. This suggests that Bunjakat participated in vast networks of exchange stretching across the Silk Road. Pigments, techniques, and artistic knowledge may have travelled thousands of kilometres before being adapted by local craftsmen. Understanding how these technologies spread remains one of the most active areas of research. How much ancient knowledge do you think was lost forever when Bunjakat disappeared, and could some of its engineering secrets still be waiting to be rediscovered? Share your thoughts in the comments below. Suzhou City Wall is one of the oldest continuously occupied urban fortification systems in China. Located in present-day Suzhou, Jiangsu province, approximately 100 kilometers west of Shanghai, the city traces its origins to 514 BCE during the spring and autumn period. At first glance, the surviving walls appear less spectacular than the Great Wall or the massive fortresses of Europe. Yet beneath the stone, brick and water lies a far deeper mystery. For more than 2,500 years, engineers, archaeologists and historians have struggled to explain how an ancient civilization built and maintained a fortified city in one of the most challenging environments imaginable. A low-lying floodplain crisscrossed by rivers, canals, and soft alluvial soils. The true mystery of Suzhou is not its walls themselves, but the sophisticated engineering knowledge hidden within a city designed to coexist with water. The ancient city was first documented in historical records associated with King Helu of the state of Wu. Archaeological investigations conducted throughout the 20th century confirm that the modern city largely follows the same urban framework established more than 25 centuries ago. Excavations uncovered sections of ancient foundations, canal alignments, and defensive structures that revealed an astonishing level of continuity. Unlike many ancient cities that shifted, expanded, or relocated over time, Suzhou remained remarkably faithful to its original plan. This persistence immediately raised a question. Why would successive dynasties preserve the same layout for over 2 millennia unless the original engineers had achieved something unusually effective? The greatest mystery surrounds the relationship between the city wall and water. Most ancient fortifications treated water as an obstacle. Moats were dug outside walls to slow attackers, but the defensive structure itself remained separate from the hydrological system. Suzhou was fundamentally different. The city functioned as an integrated hydraulic machine. Its walls, gates, canals, rivers, drainage channels, and transportation routes were interconnected into a single engineered network. Modern satellite imagery reveals that the ancient city occupied roughly 14 square kilometers. Within this area, an intricate lattice of canals distributed water throughout the urban core. The city became known as the Venice of the East, yet even that comparison might underestimate its complexity. Venice developed gradually through centuries of adaptation. Suzhou appears to have been conceived from the beginning as a coordinated system in which water management, transportation, commerce, and defense operated simultaneously. Hydrologists studying ancient urban water systems have noted that maintaining stable water levels in such an environment is extraordinarily difficult. Seasonal rainfall in the Yangtze Delta can vary dramatically. Floodwaters arriving from upstream river systems create fluctuating hydraulic pressures. Excess water threatens foundations, while insufficient water disrupts transportation and economic activity. Today, engineers rely on computerized models containing millions of data points to predict these behaviors. Ancient Suzhou possessed no such technology, yet the city functioned successfully for centuries. How did its builders calculate gradients across an enormous floodplain? How did they determine the optimal width of canals? How did they predict seasonal flow rates? No surviving technical documents provide answers. The calculations, if they existed, disappeared long ago. The mystery becomes even more intriguing at Pangate, the most famous surviving section of the ancient fortifications. Unlike conventional city gates, Pangate combined a land entrance and a water entrance into a unified defensive complex. This dual gate system allowed boats to enter the city while maintaining military security. Such a design sounds straightforward until the hydraulic challenges are considered. Water exerts enormous pressure against retaining structures. Even small differences in water level can generate forces capable of destabilizing masonry. Modern canal locks carefully manage these pressures through sophisticated engineering. Pangate appears to have solved similar problems centuries earlier. Researchers have proposed that the gate functioned as a primitive hydraulic control mechanism. By regulating the movement of water and vessels simultaneously, it may have stabilized water levels while preserving navigability. However, many original components have vanished, preventing a complete reconstruction of the system. The exact operating principles remain uncertain. Archaeologists know what the structure accomplished. They do not fully understand how it accomplished it. Another unsolved puzzle involves the city's foundations. Suzhou sits upon sediments deposited by thousands of years of river activity. Such soils are notoriously unstable. Modern engineers constructing high-rise buildings in delta environments often drive piles tens of meters into the ground to reach stable strata. Ancient builders possessed no steel piles, concrete caissons, or geotechnical surveys, yet substantial sections of the walls survived for centuries. Some reconstructed portions indicate wall heights exceeding 10 meters and widths sufficient for military patrols. The total mass of masonry and compacted earth would have reached hundreds of thousands of tons. Under ordinary circumstances, differential settlement should have produced severe cracking, tilting, and collapse. Instead, the surviving evidence suggests remarkable stability. One theory proposes that engineers created layered foundation systems using compacted earth, gravel, timber elements, and drainage materials. Similar techniques appear in certain Roman and Chinese hydraulic projects. Another theory suggests that builders intentionally distributed loads across unusually broad foundations, reducing pressure on the underlying soil. Neither explanation completely accounts for the durability observed across multiple centuries of flooding, warfare, and environmental change. The problem becomes clearer when compared with other ancient hydraulic civilizations. At Angkor in Cambodia, massive reservoirs and canals eventually became difficult to maintain as environmental conditions changed. In Venice, continuous interventions were necessary to stabilize foundations and control subsidence. Suzhou not only survived similar challenges, but maintained an operational urban environment throughout much of its history. The scale of this achievement remains difficult to quantify. Equally mysterious is the geometric precision of the city plan. Ancient surveyors lacked lasers, GPS, aerial photography, and modern cartography. Nevertheless, the arrangement of walls, gates, streets, and waterways demonstrates a degree of coordination that appears almost modern in conception. Major transportation corridors intersected strategically. Water routes connected directly to commercial districts. Defensive positions controlled access points. The entire city operated as an integrated network rather than a collection of independent structures. Some historians attribute this organization to feng shui principles and cosmological planning traditions. While cultural influences undoubtedly played a role, they do not fully explain the engineering efficiency observed in the layout. Urban planners examining historical maps have noted similarities to principles that would later emerge in modern transportation and infrastructure design. Whether these patterns resulted from empirical experimentation or sophisticated surveying methods remains uncertain. What do you think was the true secret behind the survival of Suzhou City Wall? Let us know your theory in the comments below. Gurtan Citadel stands on the edge of the central Iranian desert in Isfahan province. Built largely from earth, exposed to centuries of wind, floods, earthquakes, and temperatures that can swing more than 30 degrees Celsius between day and night, it should not still exist. Yet large sections of its walls remain standing. The fortress appears less like a ruin and more like a challenge to everything we think we know about the limits of ancient engineering. The site entered modern archaeological attention when surveys around the Varzane region revealed the remains of an enormous fortified settlement covering roughly 40 hectares. Researchers expected another abandoned desert stronghold. Instead, they found one of the largest surviving mud brick citadels in Iran, a place where ancient builders had somehow transformed Earth into a defensive system capable of surviving for centuries. The deeper archaeologists investigated, the more difficult it became to explain how a structure built from materials considered fragile today managed to outlive generations of stone buildings. The first puzzle emerges from the walls themselves. Earth is one of the oldest construction materials known to humanity, but it is also one of the most vulnerable. Water erodes it, wind strips it away grain by grain. Repeated heating and cooling create fractures that gradually weaken the structure. Modern earthen buildings often require constant maintenance to survive. Yet some sections of Gurtan have endured for hundreds of years despite prolonged exposure to the harsh climate of central Iran. Researchers studying ancient adobe architecture have discovered that long-term durability depends on an extraordinarily precise balance between clay, sand, moisture, organic fibers, and compaction techniques. Laboratory experiments show that even small changes in the ratio of clay to sand can significantly alter compressive strength and erosion resistance. Samples from Gurtan reveal carefully selected materials mixed with plant fibers and compacted into dense structural units. However, the exact formula remains unknown. It is as though the builders left behind a finished technological product but removed the instruction manual. Comparisons with other earthen cities only deepen the mystery. The great adobe metropolis of Chan Chan in Peru covers nearly 20 square kilometers, yet much of it has suffered severe weather damage. Shibam in Yemen, famous for its mud brick towers rising more than 30 meters high, survives only through continuous restoration. Even Bam Citadel, one of the largest adobe complexes ever built, experienced catastrophic destruction during the 2003 earthquake. Gurtan, although smaller, has endured environmental conditions that should have reduced it to little more than low mounds of soil. The survival rate of its walls suggests a level of practical material science that remains only partially understood. Earthquakes introduce another engineering puzzle. Iran sits on one of the most active tectonic regions on Earth. Historical records describe devastating earthquakes throughout the country's history. Conventional logic suggests that stone should be more durable than earth. Yet engineers studying seismic performance often find the opposite. Stone structures can be rigid and brittle, concentrating stress until catastrophic failure occurs. Thick earthen walls behave differently. They absorb energy, deform slightly, and distribute seismic forces across a larger mass. Some researchers believe Gurtan survived because its builders unknowingly created a giant shock-absorbing system. Others argue that centuries of observation may have taught ancient builders which construction methods performed best after earthquakes. The problem is that no surviving documents explain the reasoning. We can see the results, but the knowledge behind them has largely disappeared. The fortress layout raises further questions. Defensive architecture requires careful planning. Towers must be positioned to maximize visibility. Walls must eliminate blind spots. Gates must be protected from direct assault. Aerial surveys reveal a surprisingly sophisticated arrangement of defensive elements across the site. Distances between towers appear deliberate rather than random. Sightlines overlap. Approaches to entrances seem carefully controlled. Today, military engineers would calculate these relationships using maps, software, and mathematical models. Ancient builders relied on simple measuring tools, ropes, stakes, and direct observation. Yet the finished result demonstrates a level of geometric organization that suggests far more than trial and error. One of the most fascinating mysteries appears during the hottest months of the year. Summer temperatures in the region frequently exceed 40 degrees Celsius. Exposed surfaces can become significantly hotter under direct sunlight. Under such conditions, large enclosed settlements should become nearly uninhabitable. Yet visitors and researchers have long noted that many interior spaces within Gurten remain noticeably cooler than the surrounding environment. This phenomenon points toward a sophisticated form of passive climate control that may have been integrated directly into the architecture. Modern thermal studies provide part of the explanation. Thick earthen walls possess high thermal mass. Heat moves through compacted earth very slowly. During the day, exterior surfaces absorb solar radiation, but much of that heat takes hours to penetrate deep into the structure. By the time interior temperatures begin to rise, outdoor temperatures are already falling. The walls effectively delay heat transfer, creating a natural buffer against extreme conditions. Measurements in similar earthen buildings have shown indoor temperatures remaining 10 to 15 degrees Celsius, cooler than outside conditions during peak summer heat. Yet thermal mass alone does not fully explain Gurten. Some researchers suspect the existence of a more complex ventilation strategy hidden within the architecture itself. The arrangement of streets, courtyards, doorways, and wall openings appears capable of generating natural airflow. As hot air rises, cooler air is drawn through shaded lower areas, creating a continuous circulation cycle. Even small pressure differences can produce surprisingly effective ventilation when incorporated into large structures. In modern engineering, this principle is known as passive ventilation. Ancient builders may have discovered it through centuries of observation, without ever formalizing it into scientific theory. This possibility becomes even more intriguing when compared with the famous wind catchers of Iran. In cities such as Yazd, towering badgirs capture breezes and direct them downward into buildings, reducing indoor temperatures without mechanical cooling. Some badgirs can lower interior temperatures by more than 10 degrees Celsius. Gurten lacks the monumental wind towers that make Yazd famous, yet certain sections display environmental performance that appears surprisingly similar. This raises an unresolved question. Did the builders incorporate a less visible version of the same principles directly into the fortress design? If so, much of the cooling system may be hidden within architectural relationships, rather than obvious structures. Water management presents another challenge. No large population can survive in a semi-arid environment without a reliable water supply. Archaeological investigations have identified wells, channels, and hydraulic features associated with the settlement. However, the complete network remains poorly understood. Some scholars believe Gurten may have been connected to the ancient Persian Qanat system, one of the most impressive hydraulic technologies ever developed. Qanats transported groundwater through gently sloping underground tunnels, sometimes extending for tens of kilometers while minimizing evaporation. Certain Qanat networks have functioned continuously for more than 1,000 years. If Gurten depended on such a system, its survival may have been linked to a hidden infrastructure, stretching far beyond the visible walls. If modern engineers had to rebuild Gurten using only ancient tools and materials, do you think they could achieve the same result? Let us know your thoughts in the comments below. Kotoka rises from the flooded plains of the Bolivian Amazon, deep within the Llanos de Mojos region of northeastern Bolivia. For centuries, nothing about the landscape suggested the existence of a lost civilization. Dense vegetation concealed everything. Seasonal floods transformed the terrain into vast wetlands for months each year. To early explorers and many 20th century researchers, this appeared to be an environment incapable of supporting large urban societies. Then came one of the most surprising archaeological discoveries of the modern era. Using airborne LiDAR technology in the early 21st century, researchers stripped away the forest canopy digitally and revealed something almost impossible: an enormous engineered landscape containing monumental platforms, pyramidal structures, causeways, canals, reservoirs, defensive earthworks, and a network of interconnected settlements extending across hundreds of square kilometers. What emerged was not merely an isolated ceremonial center, but evidence of an urban civilization that challenges long-standing assumptions about the limits of ancient engineering in Amazonia. The discovery itself was remarkably recent. While archaeologists had known about the Kasarab culture for decades, through excavations of earthen mounds and settlements, the true scale of the civilization remained hidden. Traditional ground surveys could only reveal fragments. LiDAR changed everything. By firing millions of laser pulses through the vegetation and measuring their return times, scientists produced high-resolution terrain models that exposed the architecture beneath the forest. Suddenly, Kotoka appeared as one of the largest known centers of the Kasarabe culture. The site revealed massive platforms, large pyramidal structures rising approximately 22 meters high, multiple concentric defensive systems, and elevated roads stretching for kilometers across terrain that floods seasonally. The images were so unexpected that some researchers compared the discovery to uncovering a previously unknown urban tradition in the Amazon comparable in complexity to some ancient societies of Mesoamerica. What immediately captured scientific attention was not simply the size of the site, but the environment in which it was built. Most ancient urban centers developed in regions with stable agricultural land, predictable water supplies, and relatively firm ground. Kotoka existed in precisely the opposite conditions. The Llanos de Mojos is a seasonally inundated savanna covering more than 100,000 square kilometers. During the rainy season, enormous areas become flooded. Modern engineers operating in such an environment face significant challenges involving drainage, transportation, erosion control, and foundation stability. Yet, more than 1,000 years ago, the builders of Kotoka created a landscape that functioned successfully within this difficult setting. The first great mystery concerns water management. Satellite imagery and LiDAR surveys reveal extensive systems of canals, reservoirs, raised fields, and elevated causeways. Individually, each structure is impressive. Collectively, they represent one of the largest examples of prehistoric landscape modification in the Americas. Researchers estimate that thousands of kilometers of hydraulic features may have existed throughout the broader Kasarabe region. The question is how engineers without metal surveying instruments, written manuals, or modern hydrological models managed to coordinate construction on such a scale. Water flow across flat floodplains is notoriously difficult to predict because even minor elevation differences can dramatically alter drainage patterns. Modern civil engineers often rely on detailed topographic data, accurate to centimeters. The people of Kotoka somehow achieved functional hydraulic control using knowledge that remains almost entirely undocumented. Even more intriguing is the evidence suggesting that the builders did not merely react to flooding. They appear to have integrated seasonal flooding into the design of the entire landscape. Raised agricultural fields provided elevated growing surfaces. Canals may have served transportation, drainage, irrigation, and fish management functions simultaneously. Reservoirs likely stored water during dry periods, while helping regulate excess water during wet seasons. The result resembles an enormous environmental engineering project designed to transform an unstable floodplain into a productive and sustainable human habitat. Yet archaeologists still debate exactly how the system operated because no written records survive to explain its intended functions. Among all the mysteries surrounding Kotoka, perhaps none is more fascinating than the astonishing geometric precision visible throughout the settlement. When viewed from ground level, much of the architecture appears irregular due to centuries of erosion. From the air, however, a different picture emerges. Large ceremonial complexes align along carefully organized axes. Massive platforms exhibit remarkably consistent orientations. Elevated roads extend across the landscape in nearly straight lines. Causeways connect distant settlements while maintaining coherent directional relationships. Researchers have identified recurring geometric layouts suggesting deliberate planning rather than gradual organic growth. This raises a profound question. How did the builders achieve such spatial accuracy? Today, engineers use GPS systems, laser levels, total stations, and satellite imagery to establish large-scale alignments. The inhabitants of Kotoka possessed none of these technologies, yet they created linear features extending for kilometers through dense vegetation and flood-prone terrain. Some elevated roads maintain impressive directional consistency despite crossing difficult landscapes. The challenge becomes even more remarkable when one considers that surveyors often would not have been able to see the full route they were constructing due to vegetation and terrain conditions. Several explanations have been proposed. Some researchers suggest the use of astronomical observations. Ancient civilizations across the world frequently employed solar and stellar alignments to establish directional references. Others argue that repeated generations of practical surveying experience may have produced surprisingly sophisticated measurement techniques. Experimental archaeology has demonstrated that simple tools such as cords, stakes, sighting poles, and observation platforms can achieve levels of accuracy far beyond what many people assume. Nevertheless, no definitive explanation has emerged. The geometric organization visible at Kotoka continues to exceed what many scholars expected from a non-literate Amazonian society. The monumental architecture introduces another engineering puzzle. The largest structures at Kotoka include immense platform complexes and pyramidal mounds reaching roughly 22 meters in height. Unlike the stone pyramids of Egypt or Mesoamerica, these monuments were built primarily from earth. At first glance, earthen construction may seem less impressive than masonry. In reality, moving and stabilizing such enormous volumes of soil can be extraordinarily difficult. Modern earthworks require careful attention to compaction, drainage, slope stability, and erosion resistance. Without proper engineering, large earthen structures rapidly degrade. Yet many of Kotoka's monuments survived for centuries despite intense tropical rainfall. This suggests that builders possessed detailed practical knowledge regarding soil behavior. They may have selected specific soil types, layered materials strategically, engineered drainage systems, or employed compaction techniques refined over generations. The exact methods remain uncertain because erosion has obscured much of the original construction sequence. What survives is the outcome: monumental structures that endured in an environment where poorly designed earthworks would have disappeared long ago. The transportation system presents another unresolved mystery. Kotoka was not isolated. LiDAR surveys reveal an extensive network linking major and minor settlements across the region. Elevated causeways connect centers separated by considerable distances. Some roads stretch for several kilometers across wetlands and flood-prone terrain. Building such infrastructure required enormous labor investments. More importantly, it required planning. Causeways had to remain above seasonal flood levels while maintaining stable foundations. The builders also needed to coordinate routes across a landscape that changed dramatically throughout the year. Defensive architecture adds another layer of mystery. Kottaka includes concentric earthworks, moats and embankments surrounding key areas. Their exact purpose remains debated. Some archaeologists interpret them primarily as military defences. Others suggest ceremonial, symbolic, or social functions. Regardless of interpretation, the construction required substantial labour organisation. The existence of multiple defensive rings implies centralised planning and long-term investment in large communal projects. Such efforts raise important questions about governance. What kind of political system coordinated these works? How were labour forces organised? How did leaders mobilise enough people to maintain infrastructure on this scale? Trivikrama Temple is standing in the small town of Ter in Maharashtra, India, nearly 450 kilometres from Mumbai. At first glance, it looks modest compared to the giant stone temples of Khajuraho, Ellora, or Brihadiswarar. Yet hidden behind its weathered brick walls is one of the most puzzling engineering mysteries in ancient Indian architecture. Scholars estimate that the core structure was built sometime between the 2nd and 3rd centuries CE during the Satavahana period. That means parts of the building may be approaching 1,800 years in age. The mystery is not merely that it survived. The mystery is how a largely brick-built structure has remained standing through centuries of monsoon rains, extreme heat, earthquakes, religious transformation, and continuous human occupation, while many younger structures around it have disappeared completely. The temple first attracted serious archaeological attention during surveys of ancient Tagara, the historical name of Ter, a city mentioned in the ancient trade text Asterisk, Periplus of the Erythraean Sea Asterisk. Excavations and architectural studies revealed that the building was unlike almost every surviving Hindu temple in India. Instead of a conventional square sanctuary, its rear section possesses an apsidal plan, a horseshoe-shaped layout more commonly associated with early Buddhist Chaitya halls. What researchers thought would be a straightforward temple survey quickly evolved into a debate that continues today. The structure appeared to belong simultaneously to multiple architectural traditions, multiple religious identities, and possibly multiple centuries of construction. The greatest mystery revolves around the simple question of survival. Why is Trivikrama Temple still standing after nearly 2 millennia? Ancient brick structures are notoriously vulnerable. Water penetrates joints. Temperature fluctuations create microscopic fractures. Vegetation exploits weaknesses. Over centuries, entire walls can collapse. Yet Trivikrama Temple continues to preserve substantial portions of its original fabric. Maharashtra experiences annual monsoon rainfall that can exceed 700 to 1,000 millimeters depending on the region. Summer temperatures often surpass 40 degrees Celsius. These conditions accelerate deterioration in most exposed masonry. Even more remarkably, the Deccan Plateau has experienced significant seismic activity throughout history. The devastating Latur earthquake of 1993, measuring approximately 6.2 to 6.4 magnitude, damaged or destroyed tens of thousands of buildings across the region. Trivikrama Temple survived. Modern engineers examining ancient structures often focus on material science. In the case of Roman concrete, microscopic crystalline formations help explain extraordinary durability. In the case of Egyptian pyramids, massive stone blocks provide structural inertia. Trivikrama Temple offers neither advantage. Its survival appears linked to a combination of brick technology, mortar composition, geometric design, and construction precision that remains only partially understood. Analyses suggest the builders used carefully fired bricks possessing unusually consistent dimensions. Uniformity reduces stress concentration points within walls. Some researchers have proposed that organic additives, lime compounds, plant ash, or specially prepared clay mixtures may have been incorporated into the mortar. However, no universally accepted formula has emerged. The result is a structure whose longevity exceeds expectations for many contemporary brick monuments. The engineering challenge becomes even more impressive when one considers the building's age. When the temple's core was likely constructed, the Roman Empire still dominated the Mediterranean. The famous Pantheon in Rome was either under construction or only recently completed. In China, the Eastern Han dynasty was nearing its final centuries. Yet while many ancient brick structures from those civilizations survive only as fragments, substantial portions of Trivikrama Temple remain standing above ground. This comparison raises uncomfortable questions about whether certain construction techniques developed in ancient India have been lost. The geometry of the structure introduces another layer of mystery. The apsidal rear chamber is not merely decorative. Curved architecture distributes forces differently from rectangular architecture. Modern structural engineering recognizes that curved walls can redirect stress more efficiently under certain conditions. The rear semicircular form reduces stress concentrations that often develop at sharp corners. Was this intentional? Did ancient builders understand, through empirical observation, principles that modern engineering would later formalize mathematically? There are no surviving manuals explaining the calculations, yet the precision visible in the building suggests a sophisticated understanding of proportion and load management. The debate over the temple's original purpose further complicates the mystery. Early archaeologist Henry Cousins argued that the building began as a Buddhist Chaitya hall, before being converted into a Hindu temple dedicated to Vishnu. The evidence seemed persuasive. The apsidal plan, the overall spatial arrangement, and several architectural features resemble Buddhist religious structures found elsewhere in India. However, later scholars challenged this interpretation. M.S. Matta proposed that the building may have been conceived as a Hindu monument from the beginning. More than a century after the debate began, no definitive consensus exists. This uncertainty creates an intriguing technological question. If the structure truly originated as a Buddhist Chaitya, then later builders managed to transform it into a Hindu temple without compromising its structural integrity. Such a conversion would have required significant architectural intervention. Walls, entrances, decorative elements, and ritual spaces would need modification. Yet the building remained stable. How did ancient craftsmen integrate new construction phases into centuries-old masonry without creating catastrophic weaknesses? Modern restoration projects frequently struggle with precisely this challenge. The temple also demonstrates a remarkable continuity of engineering across generations. Archaeological evidence suggests that additions were made several centuries after the original construction. The front mandapa and associated elements appear to belong to a later period. This means builders separated by perhaps 300 or 400 years successfully connected new structural components to existing walls. Imagine attempting to expand a building today using techniques developed during the Renaissance while ensuring seamless integration. The achievement becomes even more impressive when viewed through that lens. Equally mysterious is the extraordinary geometric consistency visible throughout the monument. Survey measurements indicate that the curvature of the apsidal section was executed with impressive regularity. Maintaining a smooth radius across large masonry walls requires planning, measurement systems, and skilled labor. Modern builders can rely on laser instruments, computer modeling, and precision tools. Ancient builders depended on ropes, stakes, geometry, and experience. Yet the final result exhibits a level of control that suggests standardized construction methods. Where did this knowledge originate? no surviving technical documents from the Satavahana period fully explain such procedures. The location of Tare itself may provide clues. Ancient Tagara was one of the major commercial centres of the Deccan region. Trade routes connected it to ports along the western coast of India, which in turn linked to the Roman world, Arabia, East Africa, and Southeast Asia. Archaeological discoveries include Roman coins, imported goods, and evidence of long-distance exchange networks. Such connections raise the possibility that ideas travelled alongside merchandise. Architectural concepts, surveying techniques, and construction methods may have circulated across thousands of kilometres. If so, Trivikrama Temple could represent the fusion of local engineering traditions with influences drawn from one of the most interconnected trade systems of the ancient world. Perhaps the greatest mystery is why this design disappeared. If the temple represented a successful architectural form, why was it rarely copied? As Indian temple architecture evolved into the Nagara and Dravida styles, the apsidal design of Trivikrama became uncommon. Its decline suggests that a once valued architectural tradition was eventually abandoned or forgotten. Sanathi was never supposed to be found this way. In the late 20th century, workers dismantling portions of an old temple near the Bhima River in northern Karnataka, India, began uncovering carved limestone slabs hidden inside later structures. What emerged surprised archaeologists. Beneath the medieval layers lay the remains of one of the largest Buddhist centres ever discovered in southern India, a monumental stupa complex dating back nearly 2,000 years to the Satavahana period. The discovery transformed Sanathi from an obscure village into one of the most important archaeological sites in India. Yet the deeper researchers investigated the ruins, the more difficult it became to explain the engineering knowledge that had made such a complex possible. Unlike famous ancient mysteries centered on lost treasures or legends, the mystery of Sanathi is rooted in technology. How did builders working nearly 2 millennia ago create massive stone monuments, transport enormous quantities of material, achieve remarkable geometric precision, and construct foundations capable of surviving centuries of environmental stress, while leaving behind almost no record of the methods they used? The first puzzle appears in the scale of the main stupa itself. Archaeological excavations revealed that the structure originally measured approximately 36 meters in diameter, making it comparable in size to some of the largest Buddhist stupas known from ancient India. Such dimensions required not only vast quantities of stone and brick, but also an advanced understanding of load distribution. A circular monument of this scale concentrates tremendous weight toward its center. Modern engineers calculate that even a modest stone structure of similar dimensions can exert thousands of tons of downward force on its foundations. Yet, despite centuries of weathering, flooding, and human modification, large portions of the underlying platform remain stable. This is particularly surprising because the Bhima River basin consists largely of alluvial soils, sediments that are often prone to settlement and shifting. Many modern structures built on comparable terrain require deep foundations, reinforced concrete, and extensive geotechnical surveys. The builders of Sanathi possessed none of these technologies. Nevertheless, they created a platform capable of supporting a monument that survived for nearly 2,000 years. The mystery deepens when researchers examine the geometry of the site. Excavated foundations reveal an extraordinary degree of symmetry. Measurements indicate that many architectural elements maintain alignment accuracy within a few centimeters, despite spanning tens of meters. Achieving such precision without laser surveying equipment, optical instruments, or modern measuring tools remains difficult to reconstruct. Historians know that ancient Indian builders used cords, wooden measuring rods, and geometric principles described in early architectural traditions. However, the consistency observed at Sanathi suggests a level of field application that exceeds what many scholars once assumed possible. Similar precision is often associated with later achievements such as the Roman Pantheon, whose dome measures over 43 meters in diameter, or the carefully planned urban grids of Roman colonial cities. Yet Sanathi demonstrates that sophisticated geometric planning was also being applied within Buddhist architectural traditions, hundreds of kilometers from the major imperial centers of the ancient world. One of the most intriguing engineering questions concerns the stone itself. The site contains thousands of carved limestone blocks, many decorated with reliefs, inscriptions, and architectural details. Limestone may appear easy to work compared with granite, but it presents its own challenges. The material can fracture unpredictably under stress, particularly when thin decorative elements are carved into its surface. Nevertheless, the artisans of Sanathi produced relief panels featuring intricate human figures, animals, floral motifs, and narrative scenes with remarkable consistency. Some carvings exhibit straight lines, smooth curves, and symmetrical forms that would challenge even skilled stoneworkers today using hand tools. Experimental archaeology has attempted to reproduce similar work using reconstructed ancient tools. Results suggest that the labor investment required would have been enormous. The question therefore becomes not whether ancient artisans could carve the stone, but how they organized production on such a large scale. The site hints at a highly specialized workforce operating under standardized methods, yet no workshop manuals, training records, or technical texts survive to explain how this system functioned. Transportation presents another major mystery. A monument as large as the Sanathi Stupa required thousands of tons of construction material. While some stone could have been obtained locally, geological studies indicate that certain materials originated from sources located considerable distances away. Moving heavy stone blocks across ancient landscapes is never a simple task. For comparison, researchers estimate that transporting a single block weighing several tons can require dozens of workers using sledges, rollers, or draft animals. Ancient Egyptians solved similar challenges when constructing pyramids, while Romans relied on extensive road networks and specialized transport systems. Yet no comparable infrastructure has been identified around Sanathi. The Bhima River may have served as a transportation corridor, but seasonal fluctuations in water levels would have complicated navigation. The logistics necessary to coordinate extraction, transport, storage, and construction remain largely invisible in the archaeological record. What survives is the finished monument, not the technological system that created it. Perhaps the most unexpected discovery at Sanathi emerged from the carved panels themselves. Among the artifacts recovered were rare depictions associated with Emperor Ashoka, one of the most influential rulers in Indian history. These images are significant because Ashoka lived centuries before the construction of much of the visible Satavahana complex. Their presence suggests that cultural memories, artistic traditions, and possibly architectural knowledge were transmitted across vast stretches of time. This raises an important technological question. How was specialized knowledge preserved and communicated in a largely pre-industrial society? Modern engineering depends on textbooks, blueprints, formal education, and digital records. Ancient builders relied on oral traditions, apprenticeships, and practical experience. Yet the continuity visible at Sanathi implies a remarkably stable system for preserving technical expertise across generations. The monument itself may represent the surviving product of a knowledge network that has otherwise vanished completely. Researchers have also become fascinated by the orientation of the complex. Surveys indicate that major structures follow deliberate spatial arrangements rather than random placement. Certain architectural axes appear aligned with celestial events or significant solar positions. Such alignments are not unique to Sanithi. Ancient monuments from Stonehenge in Britain to Chichen Itza in Mexico demonstrate sophisticated observational astronomy. What makes Sanathi interesting is the integration of these alignments into a large religious and ceremonial landscape. Establishing accurate orientations requires repeated observations, reliable measurement systems, and long-term planning. Even small errors can accumulate over large distances. The consistency observed at the site suggests that ancient surveyors possessed methods capable of achieving a level of accuracy that continues to impress modern researchers. Another unresolved issue concerns environmental resilience. Northern Karnataka experiences intense seasonal variation. Temperatures frequently exceed 40 degrees Celsius during summer months, while monsoon rains can produce severe flooding. Such conditions are notoriously destructive to exposed masonry. Water infiltrates cracks, dissolves minerals, weakens mortar, and accelerates structural decay. Yet significant portions of the Sanathi complex endured for centuries before being buried or repurposed. Material scientists studying ancient construction techniques often emphasize that durability depends not only on materials, but also on design. Drainage systems, foundation preparation, joint construction, and load management all contribute to longevity. The surviving remains of Sanathi suggest that its builders understood these principles far better than historians once believed. Exactly how they acquired that knowledge remains unclear. Pueblito Chirama emerged from the jungle-covered slopes of Colombia's Sierra Nevada de Santa Marta during archaeological surveys of the 20th century. Located roughly 30 kilometers east of modern Santa Marta and perched hundreds of meters above the Caribbean coast, the site initially appeared to be little more than a collection of stone circles hidden beneath dense vegetation. As researchers cleared the forest, however, they uncovered something far more remarkable: an entire mountain city engineered by the Tairona civilization between approximately the 9th and 16th centuries CE. What surprised archaeologists was not the existence of another Tairona settlement. It was the level of engineering sophistication concealed beneath the jungle. Everywhere they looked, they found evidence of large-scale landscape modification, advanced drainage systems, carefully planned transportation networks, and construction techniques that continue to challenge modern understanding. Unlike many ancient mysteries that revolve around legends, lost kings, or buried treasure, the mystery of Chirama centers on a far more difficult question. How did a society without iron tools, wheeled transport, written engineering manuals, or modern surveying equipment transform one of the most challenging mountain environments in South America into a stable and functional urban center that survived centuries of tropical rainfall? The first puzzle begins with the mountain itself. Sierra Nevada de Santa Marta is one of the steepest coastal mountain systems on Earth. Rising from sea level to nearly 5,700 meters within less than 50 kilometers, the region experiences extreme topographic variation, intense seasonal rainfall, landslides, and erosion. Modern engineers often avoid large-scale construction in such environments because maintaining slope stability requires complex geological analysis. Yet the builders of Chirama accomplished exactly that centuries ago. Archaeologists have documented dozens of circular and oval terraces carved directly into steep hillsides. Some measure only a few meters across, while others exceed 20 meters in diameter. These terraces were not natural formations. They were engineered platforms created by cutting into mountain slopes and reinforcing them with carefully constructed stone retaining walls. What makes this achievement remarkable is that many of these terraces remain stable after hundreds of years of exposure to tropical weather. Modern slope stabilization projects often require concrete anchors, steel reinforcement, and sophisticated drainage calculations. The Tairona achieved comparable long-term stability using only stone, soil, and an understanding of local environmental conditions that scientists still struggle to fully reconstruct. The deeper researchers study the terraces, the more complicated the mystery becomes. Geological surveys suggest that the Tairona were not merely adapting to the landscape. In many places, they were actively redesigning it. Entire sections of hillsides appear to have been reshaped into interconnected levels capable of supporting homes, communal structures, storage facilities, and pathways. Estimates indicate that thousands of cubic meters of earth may have been moved during the construction of larger Tairona settlements. Without draft animals, carts, or metal excavation equipment, the labor requirements would have been enormous. Yet the precision of the finished structure suggests careful planning rather than gradual improvisation. The consistency of terrace dimensions across different sectors of the site hints at standardized construction principles, implying the existence of engineering knowledge that was transmitted across generations despite the absence of known written records. Perhaps even more impressive is the water management system hidden beneath the visible architecture. The Sierra Nevada receives substantial annual rainfall, often exceeding 2,000 millimeters in some regions. In mountainous terrain, such precipitation normally produces severe erosion capable of destroying poorly designed settlements within decades. Chirama should have suffered that fate long ago. Instead, archaeologists discovered evidence of sophisticated drainage infrastructure integrated directly into the urban design. Stone-lined channels guide water away from habitation zones. Terraces appear to contain subsurface drainage layers that reduce water accumulation. Pathways often function simultaneously as transportation routes and runoff control systems. During heavy rainfall, water is redirected through a network of channels before it can destabilize foundations. What fascinates hydrologists is that many elements of this system continue to function centuries after abandonment. Some researchers have compared the drainage efficiency of Tairona settlements to principles found in modern sustainable urban design, where infrastructure is engineered to work with natural water flow rather than against it. The transportation network presents another engineering enigma. Chirama was not isolated. It formed part of a larger Tairona landscape connected by stone roads, stairways, and mountain pathways extending through dense tropical forest. Certain staircases contain hundreds of stone steps that climb steep gradients with remarkable consistency. Constructing such routes would have required extensive surveying to maintain practical slopes while minimizing erosion. Modern trail engineers often rely on topographic maps, satellite imagery, and computer models when designing mountain infrastructure. The Tairona possessed none of these technologies, yet many of their routes remain usable today. The durability of these pathways suggests a sophisticated understanding of terrain mechanics, runoff behavior, and long-term maintenance strategies. Researchers continue to debate whether the road system evolved gradually or was implemented according to a broader regional plan connecting multiple settlements across the mountains. The stonework itself raises additional questions. Unlike the famous polygonal masonry of the Inca, Tairona construction relied primarily on smaller stones fitted together without mortar. At first glance, the technique appears simple. Closer inspection reveals considerable sophistication. Retaining walls often contain carefully selected stones arranged to maximize stability while allowing water to pass through. This permeability reduces hydrostatic pressure, one of the primary causes of retaining wall failure. Modern civil engineers intentionally incorporate similar principles into drainage-friendly retaining structures. The mystery is not that the Tairona discovered the technique. The mystery is how consistently they applied it across settlements separated by considerable distances. Such consistency implies shared engineering standards that archaeologists have yet to identify. Comparisons with other ancient mountain civilizations make Chiroma even more intriguing. The Inca built Machu Picchu at an altitude exceeding 2,400 meters and developed advanced terrace systems capable of resisting erosion and earthquakes. The Tairona achieved comparable environmental adaptation in a completely different ecological setting. Instead of dry Andean highlands, they operated within humid tropical forests, where vegetation growth, intense rainfall, and unstable soils create entirely different engineering challenges. Some researchers argue that surviving in the Sierra Nevada may have required an even more sophisticated understanding of hydrology than that demonstrated at many Andean sites. Yet the Tairona remain far less studied than the Inca, leaving many aspects of their technology poorly understood. One of the most fascinating discoveries involves settlement placement. Archaeological mapping indicates that Chiroma's structures were positioned according to environmental criteria that modern planners would immediately recognize. Habitation areas tend to occupy naturally stable zones with a favorable drainage. Transportation routes follow efficient contours through difficult terrain. Water management infrastructure integrates seamlessly with topography. The overall layout suggests that builders possessed detailed knowledge of geology, rainfall patterns, soil behavior, and landscape dynamics accumulated through centuries of observation. Such expertise may have been transmitted orally through specialist builders whose knowledge disappeared following the collapse of Tairona society after European contact in the 16th century. The archaeological site of Atapuerca is a place that should not have preserved so many secrets for so long. Located in the limestone hills of northern Spain, about 15 kilometers east of Burgos, Atapuerca contains one of the richest records of human evolution ever discovered. The site first attracted scientific attention in the late 19th century, when a railway trench cut through the mountains exposed a network of caves filled with ancient sediments. What began as a geological curiosity eventually became one of the most important archaeological investigations on Earth. Over the following decades, excavations revealed thousands of stone tools, animal remains, and human fossils spanning more than 1 million years. Yet despite decades of research and some of the most advanced analytical techniques available to modern science, Atapuerca continues to raise questions that archaeologists, paleoanthropologists, and engineers cannot fully answer. The mystery is not simply who lived here. The greater mystery is how some of the earliest humans in Europe demonstrated technological abilities, environmental knowledge, and organizational skills far beyond what conventional models once considered possible. The significance of Atapuerca becomes clear when compared with other famous human fossil sites. East Africa preserves some of the oldest known hominin remains, while locations such as Dmanisi in Georgia provide evidence of early migration beyond Africa. However, few places on Earth contain such a continuous record of human occupation as Atapuerca. Layers of sediment accumulated over hundreds of thousands of years, effectively creating a natural archive of human activity. These layers preserve evidence from different species, including Homo antecessor, Homo heidelbergensis, Neanderthals, and eventually Homo sapiens. In scientific terms, Atapuerca functions almost like a time machine, allowing researchers to examine technological and behavioral changes across enormous spans of time. Among the most remarkable discoveries is the site known as Grandolina. Here archaeologists uncovered fossils dating to approximately 850,000 years ago, making them among the oldest known human remains in Western Europe. The individuals associated with these remains belong to Homo antecessor, a species whose exact relationship to later humans remains debated. The fossils themselves were important, but what truly surprised researchers was the evidence accompanying them. Stone tools recovered from the same layers reveal systematic production techniques rather than random stone breaking. The toolmaker selected specific raw materials, transported them across the landscape, and shaped them according to recognizable patterns. Such behavior implies planning, knowledge transmission, and technical understanding. This raises one of Atapuerca's most fascinating mysteries. How did humans living nearly 1 million years ago identify the best stone resources without maps, geological surveys, or written knowledge? Modern analysis shows that some raw materials originated kilometers away from the caves. The distances may seem modest by modern standards, but for small groups surviving in Ice Age environments, such transport required significant effort. Researchers can identify the stone sources, but they still struggle to explain how these early populations consistently located high-quality materials generation after generation. The behavior suggests a level of environmental knowledge often associated with much later societies. Even more puzzling is the evidence of anatomical expertise found in butchered bones. Human and animal remains recovered from Grandolina contain cut marks created by stone tools. Detailed microscopic analysis demonstrates that these marks were not random. They occur at specific locations associated with muscle removal, tendon separation, and joint disarticulation. The precision resembles procedures used by skilled butchers. Some researchers interpret this as evidence of cannibalism, while others focus on what the marks reveal about technical knowledge. The individuals performing these actions possessed a practical understanding of anatomy that allowed them to process bodies efficiently. Such knowledge was acquired not through formal science but through observation and accumulated experience. Exactly how this expertise was transmitted remains unknown. Perhaps the greatest mystery at Atapuerca lies deeper underground in a chamber known as Cima de los Huesos, or the Pit of Bones. Reaching this location requires navigating a complex cave system before descending into a vertical shaft. Excavations have recovered more than 7,000 human fossils representing at least 28 individuals, all dating to roughly 430,000 years ago. No comparable concentration of Middle Pleistocene human remains exists anywhere else in the world. The sheer quantity of fossils has transformed scientific understanding of human evolution, yet the method by which these bodies arrived in the chamber remains intensely debated. The challenge is partly engineering. The chamber lies deep within a difficult cave system. Transporting bodies into such location would have required navigation through darkness, narrow passages, and vertical obstacles. Modern researchers equipped with lights and climbing equipment still find access challenging. If the accumulation resulted from intentional deposition, then the people responsible demonstrated organizational abilities far more sophisticated than traditionally attributed to humans of this era. They would have needed coordinated movement, spatial awareness, and perhaps even rudimentary planning related to death and burial. One object discovered among the fossils has fueled this debate for decades. Archaeologists found a carefully crafted quartzite hand axe nicknamed Excalibur. Unlike the thousands of bones surrounding it, the hand axe appears unique within the chamber. The artifact's red coloration and high-quality workmanship distinguish it from ordinary tools. Some researchers propose that it represents one of the earliest known symbolic offerings ever discovered. If correct, the implications are profound. Symbolic behavior is often considered a hallmark of advanced cognition. Yet if a deliberate offering occurred 430,000 years ago, then the origins of symbolic thought may extend much deeper into human history than previously believed. The cave system itself presents another technological puzzle. Navigating underground environments requires skills that are difficult to quantify archaeologically. Many passages within Atapuerca receive no natural light. Movement through such spaces demands memory, orientation, and reliable illumination. Evidence suggests repeated human use of these caves over vast periods. This raises a difficult question. How did ancient populations consistently navigate environments that modern visitors can find disorienting even with electric lighting? Some researchers speculate that long-term familiarity with cave systems produced exceptional spatial cognition. Others argue that social knowledge transmission allowed routes and landmarks to be remembered across generations. Direct evidence remains elusive. Atapuerca also challenges assumptions about survival during climatic instability. Throughout the last million years, Europe experienced repeated glacial and interglacial cycles. Temperatures fluctuated dramatically, ecosystems transformed, and animal populations shifted across the continent. Yet humans repeatedly occupied the Atapuerca region. Geological records indicate periods of environmental stress that would have tested any population's adaptability. The continued presence of human groups suggests sophisticated strategies for resource management and seasonal planning. Archaeologists can reconstruct changing climates through pollen analysis, isotope studies, and faunal remains, but the decision-making processes that enabled survival remain largely invisible. One of Atapuerca's most intriguing mysteries is how early humans preserved knowledge without writing. Despite lacking records or formal education, they passed down skills such as tool-making, hunting, cave navigation, and environmental awareness for generations. The site shows that oral traditions could effectively preserve essential survival knowledge, though exactly how this was achieved remains unclear. Adamgar Hills is a cluster of prehistoric rock shelters overlooking the Narmada Valley in Madhya Pradesh, central India. Thousands of years ago, people painted these walls, crafted stone tools with remarkable precision, and left behind traces of knowledge that still challenge archaeologists today. The site entered modern archaeology through surveys and excavations that revealed occupation layers stretching from the late Paleolithic into the Mesolithic period. Stone tools, animal remains, hearths, and rock paintings transformed what seemed to be ordinary shelters into one of the most important prehistoric archives in the Indian subcontinent. Yet the greatest mystery of Adamgar is not who lived there. It is how communities without writing, metallurgy, mathematics, or formal science develop technical skills that remain difficult to fully explain. The first clues emerge from the stone tools scattered throughout the shelters. Archaeologists recovered thousands of microliths, tiny blades, points, and geometric tools often measuring less than 5 centimeters in length. Their size is deceptive. Modern experimental archaeology has shown that producing microliths consistently requires extraordinary control over fracture mechanics. A strike delivered slightly too hard or at the wrong angle can destroy an entire stone core. Yet Adamgar produced large quantities of blades displaying similar shapes, dimensions, and manufacturing patterns. This level of standardization raises important questions. Modern manufacturing relies upon measurements, training systems, and quality control procedures. The people of Adamgar possessed none of these. Nevertheless, they repeatedly produced tools that appear almost standardized. Such consistency suggests a technical tradition preserved across generations. Whether this knowledge was transmitted through apprenticeship, ritual instruction, or some other mechanism remains unknown. The choice of raw materials deepens the mystery. Many tools were fashioned from chert, chalcedony, and quartzite. These stones behave differently when struck. Some fracture cleanly, while others contain hidden flaws that can ruin a tool. Successful production required selecting suitable material before any shaping began. Today, geologists use microscopes and laboratory analysis to understand stone properties. Prehistoric craftsmen relied entirely upon observation and experience. Yet the finished artifacts demonstrate an impressive understanding of material behavior that resembles empirical engineering. However, the most fascinating mystery at Adamgar is neither the tools nor the shelters. It is the paint. Scattered across the rock surfaces are images of animals, hunters, dancers, and scenes of daily life. Some of these paintings have survived for several thousand years. This survival should not be possible as easily as it appears. The shelters are not completely sealed caves. They are exposed to seasonal monsoons, temperature fluctuations, biological growth, wind erosion, humidity changes, and centuries of environmental stress. Under such conditions, many modern pigments begin deteriorating within decades, yet ancient images remain visible. Scientists generally agree that many of the red pigments originated from hematite, an iron-rich mineral composed primarily of iron oxide. Iron oxide is chemically stable, which explains part of the durability. But the mineral alone cannot explain everything. If powdered hematite was simply rubbed onto stone, much of it would eventually disappear through weathering. The pigment had to be attached to the rock surface through some form of binding technology. This is where this mystery begins. Researchers have proposed that prehistoric artists may have mixed mineral pigments with plant resins, animal fats, blood, tree gums, egg proteins, or other organic substances. Such mixtures could increase adhesion and improve resistance to moisture. The problem is that most organic compounds degrade over time. After thousands of years, little direct evidence remains. Scientists can analyze traces using modern spectroscopy and chemical techniques, but the original recipe remains largely lost. The challenge becomes even greater when Adamgar is compared with other famous prehistoric art sites. The paintings of Lascaux in France survive inside deep cave systems where temperature and humidity remain relatively stable throughout the year. Similar conditions exist at Altamira in Spain. Adamgar presents a different situation. Many images occupy open shelters exposed to environmental stress. In theory, they should have deteriorated much faster than European cave paintings. Their survival suggests that either the pigments were exceptionally durable, the application techniques were unusually effective, or the painters understood environmental conditions far better than modern assumptions allow. Some researchers have even suggested that repeated maintenance may have occurred over generations. If communities periodically restored fading images, the paintings would represent not a single artistic event, but a continuous technological tradition. Such a possibility would imply long-term cultural memory extending across centuries. The placement of the shelters introduces another puzzle. Several occupy elevated positions overlooking sections of the Narmada Valley. Geographic studies indicate that these locations provide broad visibility across natural movement corridors used by animals. This arrangement may have offered strategic advantages for hunting and observation. Long before satellite imagery or aerial mapping, prehistoric inhabitants selected locations that maximized awareness of the surrounding landscape. Their decisions reflect a sophisticated understanding of terrain, ecology, and animal behavior. The Narmada Valley itself was one of the most important prehistoric corridors in South Asia. Human populations moved through the region for hundreds of thousands of years. Adamgar, therefore, was not an isolated site, but part of a larger network of communities. Archaeologists increasingly suspect that ideas, technologies, and survival strategies may have circulated across vast distances. The standardized tool technologies found at Adamgar could represent the visible remnants of information networks that disappeared long ago. The paintings offer another glimpse into the cognitive world of these ancient people. Many scenes depict coordinated group activities rather than isolated individuals. Hunting scenes involve multiple participants. Social gatherings appear organized rather than random. Such imagery suggests planning, communication, and collective memory. In a world without writing, paintings may have functioned as information storage systems. They could preserve stories, knowledge, hunting strategies, or cultural traditions in visual form. Evidence from later occupation layers suggests gradual contact with domesticated animals and early agricultural practices. Yet the transition appears slow and complex. Rather than replacing hunting overnight, new technologies seem to have merged with existing ways of life. This pattern resembles technological evolution rather than technological revolution, revealing communities capable of adaptation and experimentation over long periods. Do you think the durability of Adamgar's paintings came from a lost pigment formula, or from generations of artists continuously maintaining the images? Share your thoughts in the comments below. Avaldsnes sits on Karmøy Island on the western coast of Norway, overlooking the narrow Karmsundet Strait. Archaeological investigations began in the 19th century, but major excavations during the 20th and 21st centuries transformed understanding of the site. Beneath medieval structures and royal estates, archaeologists uncovered evidence of elite Viking settlements, monumental halls, harbours, workshops, burial sites, and centuries of continuous occupation. The discoveries revealed that Avaldsnes was not simply a village. It was one of the most important centres of power in Viking Age Scandinavia. What makes Avaldsnes remarkable is not only its historical importance, but also the possibility that the site functioned as a technological and logistical hub, whose capabilities still challenge modern understanding of Viking engineering. The first mystery begins with geography. Avaldsnes occupies an almost impossibly strategic location. The settlement overlooks Karmsundet, a narrow shipping corridor that stretches along Norway's western coastline. During the Viking Age, this strait served as one of the safest routes for ships travelling between northern and southern Scandinavia. At certain points, the channel narrows to only a few hundred metres, meaning any vessel moving through the region would have been visible from Avaldsnes. Modern geographic analysis suggests that few locations along the Norwegian coast provide such complete control over maritime traffic. The position allowed rulers to monitor trade, collect taxes, regulate movement, and project military power across enormous distances. The mystery is how Viking leaders identified this location so precisely. Today, strategic maritime planning involves satellite imagery, topographic surveys, and geographic information systems. Yet more than 1,000 years ago, the founders of Avaldsnes selected a position that maximized visibility, accessibility, and control with extraordinary efficiency. Was this merely experience accumulated over generations? Or did Viking navigators possess sophisticated surveying methods that archaeology has yet to identify? Excavations have revealed traces of enormous Viking longhouses associated with elite rulers. Some structures exceeded 40 metres in length. For comparison, many ordinary Viking houses measured less than 15 metres. These halls were among the largest wooden buildings constructed in Northern Europe during their time. Building on such a scale created significant engineering challenges. Western Norway experiences powerful Atlantic storms, strong winds, heavy rainfall, and seasonal snow loads. A roof spanning dozens of meters required careful load distribution and structural stability. Unlike modern architects, Viking builders had no steel reinforcements, no concrete foundations, and no engineering software. Yet many of these structures remained functional for generations. Experimental archaeologists attempting to reconstruct Viking halls have discovered that even minor mistakes in pillar placement can destabilize entire roof systems. The fact that the original halls survived suggests their builders understood complex structural principles. The mystery is that no written construction manuals survive. The halls demonstrate advanced practical engineering, but the knowledge behind their design appears to have disappeared. Perhaps no mystery surrounding Avaldsnes is more significant than its connection to Viking ships. The power of Avaldsnes depended entirely upon control of maritime routes. Such control required fleets capable of moving warriors, goods, livestock and resources across thousands of kilometers of coastline. The Viking longship remains one of the most efficient wooden vessels ever built. Archaeological evidence from famous ships such as the Oseberg ship and Gokstad ship demonstrates astonishing technical sophistication. Their clinker-built hulls combined flexibility with strength, while their shallow drafts allowed navigation of rivers and survival during open ocean voyages. Modern naval architects studying reconstructed Viking ships have repeatedly noted how effective their designs are. Computer simulations suggest that some longships achieve speeds exceeding 15 knots under favourable conditions, and certain replicas have demonstrated remarkable seaworthiness in North Atlantic waters. Yet a fundamental mystery remains. How did Viking shipbuilders determine the optimal hull shapes? Modern vessel design relies heavily on hydrodynamic calculations, fluid modelling and extensive testing, but Viking builders had none of these tools. Some researchers believe the designs evolved purely through trial and error, while others argue that generations of accumulated engineering knowledge may have formed a sophisticated but unwritten system of design rules. If such a system existed, Avaldsnes would likely have been one of its most important centres. Avaldsnes stood at the centre of a maritime network extending from Scandinavia to Iceland, Greenland and North America. These voyages required extraordinary navigational abilities. The distance from Norway to Iceland exceeds 900 kilometres, and Greenland lies even farther west. Successful crossings demanded accurate orientation over vast stretches of ocean, where land remained invisible for days. One of the most debated mysteries involves the legendary Viking sunstone. Several medieval texts describe special stones capable of locating the sun even under cloudy conditions. Modern experiments using Iceland spar, a transparent calcite crystal, have shown that polarized sunlight can indeed reveal the sun's position when hidden by clouds. The results surprised many researchers. Laboratory studies demonstrated that the technique could potentially improve navigation accuracy significantly in northern latitudes where weather conditions are often poor. However, direct archaeological evidence remains limited. Did Viking navigators actually use such technology, or are modern researchers projecting scientific explanations onto medieval legends? Avaldsnes, as a centre of royal maritime activity, would have been one of the most likely places for such navigational knowledge to develop and spread. Another mystery involves the broader landscape surrounding Avaldsnes. The region contains burial mounds, standing stones, monuments, ancient roads, and ceremonial sites arranged across the terrain. Many appear positioned with remarkable intentionality. Some researchers suggest that these features may have served practical functions in addition to religious or political roles. Large monuments could have acted as navigation markers visible from ships approaching the coastline, while certain elevated positions provided long-distance sightlines across the strait. If correct, The landscape itself may have functioned as a form of infrastructure. Long before lighthouses appeared, Viking sailors may have relied on carefully placed landmarks integrated into the environment. This possibility raises important questions. Who designed these systems, how were locations selected, and how was knowledge of their purpose transmitted across generations? The answers remain uncertain. Avaldsnes also reveals evidence of iron production and metalworking. To modern observers, ancient ironworking may seem relatively simple, but in reality producing usable iron is an extraordinarily complex process. Bloomery furnaces must reach temperatures approaching 1,200 degrees Celsius, and operators must control airflow, fuel quality, furnace dimensions and ore composition with remarkable precision. Even small errors can dramatically reduce efficiency. Archaeological remains suggest that Viking smiths repeatedly achieved successful production on a large scale. The mystery is how. Without thermometers, pressure gauges, or modern measuring equipment, ancient metalworkers somehow optimized systems that modern experimental archaeologists often struggle to reproduce. Many reconstructed furnaces fail repeatedly before achieving results comparable to archaeological examples. This suggests that Viking metallurgists possessed practical knowledge far more sophisticated than surviving evidence can fully explain. Perhaps the most overlooked mystery concerns administration. Avaldsnes functioned as a royal centre connected to territories spread across enormous distances. Maintaining authority required communication. Orders had to travel, taxes had to be collected, military forces had to be mobilised, and trade had to be regulated. Today, such tasks depend on telecommunications, roads, and digital systems, yet Viking rulers possessed none of these advantages. Historical sources nevertheless indicate that they successfully coordinated activities across large portions of Scandinavia. Some researchers propose networks of signal fires, relay stations, and maritime communication routes, while others believe personal relationships and decentralized governance played a larger role. Regardless of the explanation, the logistical achievement remains extraordinary. What do you think? Were the achievements of Avaldsnes simply the result of generations of experience? Or did the Vikings possess engineering and navigational knowledge that has been largely lost to history? Let us know your thoughts in the comments below. Standing beside the ancient Aurelian walls is one of the strangest monuments in the entire Roman world. It is not a temple, it is not an amphitheatre, and it is not a triumphal arch. It is a pyramid. Known as the Pyramid of Cestius, the structure rises approximately 36.4 meters, 119 feet high, with a base measuring about 29.5 meters, 97 feet on each side. Built around 1812 BC as the tomb of the Roman magistrate Gaius Cestius, it remains one of the best preserved monuments from ancient Rome. Its existence alone raises questions. Why would Romans, famous for arches, domes, roads, and aqueducts, suddenly construct an Egyptian-style pyramid in the heart of Italy? Yet the deeper archaeologists investigate, the more extraordinary mysteries emerge, not merely about its purpose, but about the engineering knowledge required to build it. An inscription on the monument reveals a remarkable detail. The pyramid was completed in just 330 days. At first glance, this may not sound extraordinary, but consider what the project involved. Workers had to prepare foundations, construct a massive concrete core, produce enormous quantities of brickwork, transport marble from distant quarries, shape the exterior, decorate the burial chamber, and complete all finishing work within less than a year. Modern engineering studies estimate that the structure contains thousands of tons of construction material. For comparison, many modern public buildings of similar size often require significantly longer construction schedules, Despite cranes, trucks, power tools, and computer planning systems, ancient Roman builders possessed none of these advantages. How they organized labor, coordinated material deliveries, and maintained such speed remains poorly understood. Some historians estimate that hundreds of workers may have operated simultaneously. Others suggest that the Roman Empire's logistical systems were so efficient that materials could move through supply networks with a speed rarely associated with ancient civilizations. Whatever the explanation, the construction schedule remains one of the most astonishing aspects of the monument. The Pyramid of Cestius appears Egyptian on the outside. Inside, however, it is entirely Roman. Unlike the Great Pyramid of Giza, which consists of millions of limestone blocks, the Pyramid of Cestius relies primarily on a concrete core covered with brick and marble. This concrete, known as opus caementicium, continues to fascinate scientists today. Modern laboratory studies have revealed that Roman concrete often contains volcanic ash, lime, and mineral compounds capable of producing self-healing reactions when cracks develop. Researchers studying Roman harbour structures have discovered examples that remained durable for nearly 2,000 years despite constant exposure to seawater. The Pyramid of Cestius demonstrates a similar level of durability. For over 2,000 years it has survived earthquakes, storms, pollution, urban expansion, military conflicts, and environmental degradation. Many modern concrete structures begin showing major deterioration after only 50 to 100 years. The Pyramid of Cestius continues standing after 20 centuries. Scientists can identify many of the ingredients used by Roman builders. What remains unclear is whether the Romans fully understood the long-term chemical reactions occurring inside their concrete, or whether they achieved these results through generations of practical experimentation. Either possibility suggests a level of material science far more sophisticated than commonly assumed. The pyramid's steep sides rise at angles far sharper than most Egyptian pyramids. Maintaining symmetry over a height exceeding 36 meters required extraordinary precision. Today, engineers use laser levels, GPS systems, digital surveying equipment, and computer modeling. Roman builders relied on ropes, plumb bobs, measuring rods, and geometry. Yet modern surveys reveal remarkably accurate alignment and symmetry. This raises a fundamental question. How much mathematical knowledge did Roman surveyors possess? Roman engineers are known to have mastered land surveying techniques. They designed roads crossing entire continents, aqueducts maintaining gradients of only a few centimeters per kilometer, and military camps with highly standardized layouts. The Pyramid of Cestius may represent another example of lost practical knowledge. The structure suggests a sophisticated understanding of geometry and construction control, yet very little technical documentation survives explaining exactly how such precision was achieved. One of the most overlooked mysteries involves the monument's white marble exterior. The entire structure was originally covered with fine Carrara marble. This stone originated hundreds of kilometers away in northern Italy. Extracting the marble required quarrying operations. Transporting it required roads, rivers, ships, carts, workers, animals, and administrative coordination. Every block had to arrive at the correct location and at the correct stage of construction. The logistics become even more impressive when viewed within the 330-day construction deadline. For comparison, the construction of Egyptian pyramids required enormous transportation systems. The builders of the Parthenon in Athens faced similar challenges. The Roman Empire appears to have developed an equally sophisticated supply network. Yet historians still debate the true scale of Roman construction logistics because the documentation is fragmentary. The Pyramid of Cestius may represent only a tiny surviving example of a system far larger than archaeologists can currently reconstruct. Within the monument lies a small burial chamber measuring approximately 5.95 meters long, 4.10 meters wide, and 4.80 meters high. The chamber contains delicate frescoes painted on white backgrounds. Its size presents an interesting contradiction. An enormous pyramid surrounds a relatively modest burial room. This raises questions about symbolism. Was the pyramid intended primarily as a tomb? Or was it also a public statement of wealth, power, political status, and cultural influence? Many details of the original interior remain unknown because grave robbers likely entered the structure centuries ago. Artifacts that might have explained the owner's intentions are largely missing. The surviving chamber therefore preserves only fragments of the monument's original story. Perhaps the greatest historical mystery concerns the design itself. The pyramid was built shortly after Rome's conquest of Egypt in 30 BC. Egyptian culture suddenly became fashionable among Roman elites. Obelisks appeared throughout Rome. Egyptian religious practices gained followers. Artistic styles spread across the empire. Yet the Pyramid of Cestius remains unique. Romans constructed countless tombs, but almost none adopted such an extreme Egyptian form. Why did Gaius Cestius choose a pyramid instead of a traditional Roman mausoleum? Some scholars suggest it reflected admiration for Egypt. Others believe it symbolized prestige and international influence. Still others argue that the shape carried religious meanings now lost to history. The absence of written explanations means the true motivation remains uncertain. The monument's continued survival presents another puzzle. Over 2,000 years, Rome experienced invasions, civil wars, earthquakes, economic collapse, medieval rebuilding, and modern urban development. Many ancient structures vanished completely. The Pyramid of Cestius endured. Its survival was partly accidental. During the construction of the Aurelian walls in the 3rd century AD, the pyramid was incorporated into Rome's defensive system. This decision protected the structure from destruction. Yet preservation alone does not explain its durability. The monument still depends on engineering decisions made more than 20 centuries ago. The foundations continue supporting immense weight. The concrete remains stable. The geometry remains intact. Every surviving feature points toward a level of practical engineering expertise that historians can observe but not fully reconstruct. Archaeological lies near the modern town of Monreal de Arisa in Zaragoza province, northeastern Spain. Today, only ruins remain scattered across a strategic hill overlooking the Jalón Valley. Archaeological investigations during the 20th century reveal that beneath the soil existed the remains of a significant Celtiberian settlement that later became a Roman city. Excavations uncovered streets, residential districts, public buildings, water systems, cisterns, and one of the most remarkable discoveries at the site, a Roman bath complex. These findings confirmed that Archaeological was not a simple provincial settlement, but a carefully planned urban centre integrated into the Roman world. Yet, the discoveries also created a series of mysteries that remain only partially understood. Nearly 2,000 years later, archaeologists continue asking how a city built on such difficult terrain could sustain sophisticated infrastructure, manage water supplies, and maintain engineering systems that rival those found in much larger Roman settlements. The first mystery begins with geography itself. Most successful Roman cities were founded near rivers, fertile plains, or major transportation corridors. Archaeological occupied a hilltop position that offered defensive advantages, but created enormous engineering challenges. Building a city on sloping terrain requires solutions for drainage, foundations, transportation, and water management. Modern engineers facing similar conditions rely on surveying instruments, topographic mapping, computer modeling, and advanced construction equipment. The inhabitants of Archaeological possessed none of these technologies, yet archaeological evidence suggests they created a remarkably organized urban environment. Streets followed carefully planned routes, buildings were arranged to maximize available space, and public infrastructure appears integrated into the landscape rather than imposed upon it. Researchers estimate that Roman surveyors could achieve surprising levels of accuracy using instruments such as the groma and chorobates. Experimental archaeology has demonstrated that Roman land surveyors were capable of maintaining alignments over distances exceeding several kilometers, with errors often measured in mere centimeters per 100 meters. But exactly how the planners of Archaeological adapted those techniques to a rugged hilltop environment remains uncertain. The city appears to have been designed according to principles that required precise measurements, yet the methods used to implement those measurements on uneven terrain remain largely invisible. Perhaps no question surrounding Archaeological is more important than water. Every Roman city depended upon reliable water supplies. Water was required for drinking, cooking, sanitation, industrial activities, fountains, and baths. The problem is obvious. Archaeological sits above the surrounding landscape, and gravity naturally favors settlements located below water sources, not above them. Excavations have uncovered cisterns, reservoirs, drainage systems, and hydraulic infrastructure. The existence of these facilities proves that significant quantities of water reach the city. What remains unclear is exactly how. Some researchers suggest that nearby springs may have supplied the settlement. Others believe portions of a water transport network remain undiscovered. Still others propose sophisticated rainwater collection systems. The challenge becomes even greater when considering consumption rates. Studies of Roman bath complexes indicate that even modest baths could consume tens of thousands of litres of water daily, while larger facilities throughout the empire sometimes processed hundreds of thousands of litres. If Archaeological's bath complex operated regularly, the city required a supply system capable of delivering substantial volumes of water continuously. Yet no fully preserved aqueduct has been identified. This creates a technological puzzle. The infrastructure clearly existed, the water clearly arrived, and the engineering system clearly functioned. But key parts of the mechanism remain missing. The discovery of the baths revealed another mystery. Roman baths were among the most technologically advanced structures of the ancient world. They were not simply pools of warm water, but carefully engineered thermal systems. A typical Roman bath included multiple chambers maintained at different temperatures. Visitors moved between cold rooms, warm rooms, and hot rooms, and achieving this required remarkable control over heat transfer. The secret was the hypercaust. This system used elevated floors supported by hundreds of small pillars. Hot air generated by furnaces circulated beneath the floors and through hollow wall spaces, heating entire rooms. Modern studies of reconstructed hypercaust systems have demonstrated interior temperatures exceeding 40 degrees Celsius, and some experiments suggest floor temperatures could approach 50 degrees Celsius directly above heating channels. At Archaeological, archaeologists found evidence that such technology existed, but several questions remain unanswered. How much fuel was required to maintain operation? How many workers managed the furnaces? How was airflow regulated? How did engineers prevent structural damage caused by repeated heating and cooling cycles? Even modern engineers recognize that thermal management is a complex challenge. Materials expand and contract, heat distributes unevenly, and moisture affects durability. Roman builders solved these problems with remarkable success, yet the technical knowledge behind their solutions was almost entirely lost. Archaeological experienced significant seasonal temperature variations. Summers in northeastern Spain can be extremely hot, while winters can become surprisingly cold. This environmental challenge may explain another engineering mystery. Many Roman buildings appear designed to regulate indoor temperatures naturally. Archaeological evidence suggests thick masonry walls, strategic building orientation, and carefully designed ventilation systems may have contributed to passive climate control. Modern sustainable architecture often relies upon similar principles. Thermal mass stores heat during the day and releases it gradually at night. Air circulation improves comfort without mechanical systems, and building orientation influences solar exposure. What makes Archaeological fascinating is that these principles may have been applied nearly 2,000 years ago. Because upper sections of most structures have disappeared, researchers cannot fully reconstruct the original designs. As a result, the extent of Roman climate engineering remains a subject of ongoing investigation. Every stone visible at Archaeological raises another question. How did it get there? Many construction materials had to be transported uphill. Large stone blocks required extraction, shaping, transportation and placement. Even with modern equipment, moving heavy stone over uneven terrain is challenging. The Romans accomplished such tasks throughout the empire. At sites like the Colosseum, engineers transported stones weighing several tons, while at Baalbek, Roman builders worked with blocks exceeding 800 tons. Archaeological operated on a smaller scale, but the logistical principles remain impressive. Researchers estimate that a single large construction project could require thousands of individual transport operations. Draft animals, wooden sledges, rollers, cranes, and human labor likely played essential roles. However, very little direct evidence survives regarding the specific construction techniques used at Archaeological. The buildings survive, but the machines do not. Perhaps the most overlooked mystery is surveying. Before any building could be constructed, engineers had to understand the landscape. Modern surveyors use GPS satellites capable of determining positions within centimeters, while Roman surveyors relied upon geometry, observation, and experience. Yet archaeological evidence throughout the Roman Empire demonstrates astonishing accuracy. Roads maintained straight alignments over vast distances. Aqueducts preserved gradients measured in centimeters per kilometer, and urban layouts followed carefully organized plans. Archaeological was part of this tradition. Its streets, infrastructure, and public spaces indicate systematic planning rather than random growth. But no engineering manuals from Archaeological survive. No blueprints exist. No project reports explain how measurements were taken. Only the results remain. What do you think? Did the engineers of Archaeological possess practical techniques that have been completely lost to history? Or will future discoveries eventually reveal the secrets behind this remarkable hilltop city? Let us know your thoughts in the comments below. Gamla Uppsala lies approximately 5 kilometers north of modern Uppsala in central Sweden. Today, it appears as a peaceful landscape dominated by 3 enormous burial mounds, but archaeological excavations have revealed that this site was once one of the most important political and religious centers in Scandinavia. The first systematic investigations began in the 19th century, while major archaeological excavations during the 20th and 21st centuries uncovered royal halls, ritual structures, ancient roads, workshops, and evidence of large-scale construction projects. Ground-penetrating radar, geophysical surveys, aerial mapping, and modern excavation techniques continue to reveal previously unknown features hidden beneath the landscape. What researchers discovered raised an unexpected question. How did a society living more than 1,500 years ago create engineering projects on a scale that would challenge even many medieval kingdoms centuries later? Unlike famous ancient mysteries such as the Egyptian pyramids or Stonehenge, Gamla Uppsala is not known for giant stone monuments. Its mysteries are hidden within earthworks, timber architecture, logistics systems, and construction techniques that remain only partially understood. The most recognizable features of Gamla Uppsala are the 3 monumental burial mounds known as the Royal Mounds. Each mound rises roughly 9 to 10 meters high and measures approximately 55 to 70 meters in diameter, and archaeologists date their construction to the 5th and 6th centuries AD. At first glance, they may appear simple compared to the pyramids of Egypt, yet engineering calculations suggest otherwise. Building a single mound required moving thousands of tons of earth, clay, gravel and turf, and the 3 mounds together represent one of the largest earth-moving projects in Northern Europe during the migration period. The challenge becomes even more impressive when considering the available technology. No wheeled construction equipment existed, no iron excavators existed, and no modern surveying instruments existed. Researchers estimate that tens of thousands of cubic meters of material had to be collected, transported, shaped, and compacted. Even today, civil engineers understand that large earthen structures require careful control of slope angles and drainage. Poorly designed mounds erode quickly, yet after nearly 15 centuries the royal mounds remain remarkably stable. How their builders achieve such durability remains an active subject of investigation. Perhaps the most surprising discoveries at Gamla Uppsala are the remains of gigantic wooden halls. Excavations have revealed structures exceeding 50 meters in length, and some researchers compare them to royal halls described in early Scandinavian legends and sagas. Constructing buildings of this scale required technical knowledge far beyond simple carpentry. Massive roof systems had to support significant loads during harsh Scandinavian winters, and snow accumulation alone could place enormous pressure on timber structures. Modern structural engineers rely on mathematical calculations and computer modeling to predict these forces, but the builders of Gamla Uppsala possessed neither. Yet archaeological evidence suggests that these halls stood for decades and possibly generations. This raises several unanswered questions. How were suitable trees selected? How were load-bearing beams designed? How did builders prevent structural collapse? And how was construction knowledge transmitted without written engineering manuals? The answers remain largely unknown because the buildings themselves have vanished, leaving only post holes and fragments behind. One of the most astonishing discoveries in recent years involved rows of enormous timber posts stretching across the landscape. Archaeologists identified hundreds of post holes, indicating the existence of large wooden pillars that once formed extensive linear structures, and some stretches may have extended for more than a kilometre. The purpose of these posts remains debated. They may have marked ceremonial routes, defined sacred boundaries, symbolized royal authority, or served multiple functions simultaneously. What is certain is the engineering challenge involved. Many of these posts were likely cut from mature trees weighing several tons, and transporting them without modern machinery would have required coordinated labor forces and sophisticated planning. Experimental archaeology has demonstrated that moving and erecting large timber pillars is extraordinarily difficult, even when modern teams possess detailed engineering knowledge. Yet the builders of Gamla Uppsala completed these projects repeatedly. Exactly how they accomplished this remains unclear. Perhaps the least appreciated mystery concerns measurement and planning. Modern aerial surveys reveal that Gamla Uppsala was not a randomly developed settlement. The burial mounds, halls, roads, ritual spaces, and post alignments appear to form an organized ceremonial landscape, and creating such a landscape required accurate surveying. Today, engineers use GPS systems, laser levels, satellite imagery, and digital mapping software. The builders of Gamla Uppsala had none of these tools. Nevertheless, they managed to position structures across large distances with impressive consistency. This mystery resembles challenges found at other ancient sites. The builders of Stonehenge aligned monuments with celestial events. The engineers of the Roman Empire created roads extending thousands of kilometers, and the creators of Machu Picchu organized architecture across difficult mountain terrain. Gamla Uppsala presents a Northern European version of the same puzzle. What surveying methods allowed such precision? No surviving documents provide answers. Engineering is not only about construction, it is also about organization. Many historians believe Gamla Uppsala functioned as a major political and religious center attracting visitors from across Scandinavia. If this interpretation is correct, the logistical implications are enormous. Large gatherings require food supplies, water, transportation systems, storage facilities, and administration. The challenge becomes clearer when compared to later medieval cities. Supporting thousands of temporary visitors demands a complex supply network extending far beyond the settlement itself. Archaeological evidence suggests that Gamla Uppsala occupied a strategic position connected to regional trade routes and fertile agricultural lands. Yet researchers still do not fully understand how such a system operated. The infrastructure that sustained the site has largely disappeared. Unlike Egypt, where stone monuments survive for millennia, Scandinavian societies built primarily with wood. This creates a unique archaeological problem because wood preserves poorly. As a result, much of the technological knowledge behind Gamla Uppsala may have vanished completely. Ancient builders likely understood timber selection, drying methods, structural behavior, joinery techniques, and long-term maintenance. Modern carpenters know that different tree species behave differently under stress, that moisture content affects strength, that grain orientation influences durability, and that joint design determines stability. The people of Gamla Uppsala clearly mastered these principles in practice, yet almost no written evidence survives explaining their methods. Researchers can study the results, but the knowledge itself remains largely lost. Another debate concerns astronomy. Some researchers have proposed that elements of Gamla Uppsala's layout may relate to solar observations or seasonal cycles. Similar theories have been investigated at Stonehenge, Newgrange, Chaco Canyon, and numerous ancient ceremonial centers around the world. Supporters argue that agricultural societies often depended on accurate seasonal knowledge, while critics caution that many proposed alignments may be coincidental. At present, definitive evidence remains elusive. However, if future research confirms intentional astronomical planning, it would reveal another layer of technical sophistication within the site's design.